Okay. So today we're going to be talking about everyone's favorite topic, which is airplane crashes, and why they do or do not happen. It's a great topic. It's going to tie into a lot of the things that we've discussed throughout the past week and a half or so. So what I'm going to ask is that if you have any questions, do raise your hand, but I'm going to take them at the end, just so we can get through the material without interruption. The questions are a lot more informative, so having them together, not to mention that your question might be answered on the next slide. So let's get started. This is well-known fact, surprise to no one, but air travel is statistically the safest mode of travel. Depending on how you look at it, elevators might technically be safer. I know in New York City, over the past century or so, two of the major accidents involving elevators have been due to um, an airplane striking the building, once in 1946, and then again in more recent unfortunate memory. But there have been dramatic improvements since the 1970s, since the mid 1970s, and those improvements have been paying off dividends left and right. And they were in, and improvements are even being made, to this day. Um, we're going to primarily focus on what is called a FAA Part 121 airline. So that is the sort of airlines that we're all familiar with. So that's like Delta, Southwest, British Airways, Air France, Emirates, things like that. Less than some of these one-off charter commuter airlines, which is we're including things like like your connecting regional jet sort of flights, but these are usually more prop liners, one-offs. They operate under a different set of rules. However, their fatalities will be included in the next plot, um, which will drive the point in even more. But the U.S. went let's see, sorry, nine over 9 years without having a single passenger fatality on board an aircraft. If you were on an airplane, a passenger airplane in the United States, and you died, it was probably because of heart disease or smoking or alcoholism or any of the things that were talked about in the previous lecture. Um, and there were no what's called a hull loss accident, and that means that a plane crashes so hard you can't fly the plane again. There are actually accidents with, in 99% of the time, there are no fatalities, no injuries at all. There have been accidents with injuries and fatalities where the aircraft returned to service and was able to fly again. But a hull loss is, the sort of thing that you see on the news, the wreckage strewn about everywhere, and there was not one on U.S. soil. Um, between 2013 until unfortunately February. I had to update these slides last week because uh, we hadn't had one since the previous worry. Um, and there have been, if you look at just U.S. airlines, not just, accidents from other air carriers, because that 2013 accident was actually a Korean airline in San Francisco. The record is absolutely fantastic. It went from 2018 until February of this year without a single fatality on board a U.S. aircraft. And we'll get into both of those. So, um, if you take a look at the safety by mode of transportation, these are fatalities by passenger mile, and then or 100 million passenger miles, and then also by hourly rate as well. And these come from the Bureau of Transportation Statistics, which is a part of the DOT. So these are really good numbers. And if you look at the blue, those are cars on the highway. You can't even see, well, actually, air travel doesn't even show up on some of the years. And when it does, you can barely see it. These are pixels we're talking about. Um, the next that you see is rail as the second most dangerous. And the vast majority of people who are killed by rail are people in their car driving on the crossings. So again, transportation within the United States is absolutely fantastic in terms of safety.
US scale, I think the risk of rail in Europe is vastly different. But yeah, you're right.
Yeah, it's uh So the per mile risk of flying is less than 1% the risk of driving on the highway. When I was doing some research, Wikipedia, by a certain calculation, found that flying was 750 times safer. Now, how they calculate that, they didn't really give a good source on if that's per passenger mile, embarked passenger per hour. But the point stands is that you're nitpicking at that point. So, in order for an aviation system to be safe, it must have really, it's got to be something capable of frequent operation, because there's no such thing as a perfect system, and the whole point of testing is to reveal outliers before it goes into operation and is putting property and people at risk. So you have to be able to operate it very frequently. The more complicated a system is, the more chances there are for risk on board. A healthy regulatory environment is essential for analysis and validation. You can't just design it and say, okay, it's good to go. You need to have independent people checking off. Even if you did a fantastic job and got everything perfectly right, you want someone else to say that you also got it right as well. Imagine, you don't want to like, imagine going to a show and there's a comedian and no one's clapping. It's that external validation is critical. And a lot of it does also come to accountability and safety culture being absolutely critical. The mind frame that accidents will happen, that doesn't make them acceptable, but there needs to be, a thorough investigation to figure out what went wrong, because there's always going to be multiple things. So on this slide, we have two blocks of images showing things that are at the opposite end of the spectrum. So we have the 737 MAX, which was not subject to there were cultural reasons why it began failing. The regulatory environment fell apart and the thing started crashing. You have the space shuttle and you have the Hindenburg as well. These things that flew, once every, couple of months. Space shuttle flew 135 times. Airships had, maybe hundreds of flights in their heyday at most. And they never had the rigor applied to them where they were able to flesh out all of the issues with them. And then when the issue did pop up, it was always in a very dramatic way and was either not fixed for future flights, or it was the end of the program then and there. On the other side, you have the A320 new engine option. You've got a Falcon 9, you've got a Cessna 172. The number of pilots in the world who have not flown on a Cessna 172, you could probably count on your fingers on one hand after a knife accident. The Falcon 9 has recently gone into the 99.5% reliability rate. This thing is flying 2 times a week sometimes, which is absolutely unheard of for a spacecraft. And the reason why is that every single component on there gets tested individually, but then the thing is flying so often, when the issues popped up early in the program and they were able to get rid of them. And then you have, the A320 was an incremental upgrade to an older aircraft, but it was focused more on efficiency and weight and the engines and the wing. They didn't try to force or shoehorn anything in there that was unacceptable for something of an aircraft of that age. So here are the transportation safety numbers. This is a plot that shows total fatalities worldwide um, on embarked passengers. And then it also shows the number of people who have flown every year. And you can see that, you know, air travel grows every year. There's one exception from 5 years ago. I'll let the reasons why be an exercise for the reader to determine. But you can see, the overall trend of air crashes is going down. And if you look at the years where there's an increase from the previous year, it's almost always driven by one or maybe two particular instances. There's a theory, I think, about that out there about one thing dominating the statistics for a period of time. But I think there's a book. You can look it up. It's probably on Amazon. Um, so this was a graphic that showed how 2023 was the safest year for air travel to date. This came from the International Association of Air Transportation. 2024 had an increase It was slightly more risky, but still better than the 5-year average and significantly better than the previous 50 years. So, in order to make aircraft safe, flying safe, you have to, or these complex systems involved with them, you have to have one of two types of robustness in there, and that is fault resistance or fault tolerance. And trees are a really good example of what I'm talking about here. So, fault resistance means that you are designed to take any stress applied to the system and be able to come out on the other side intact. So a tree trunk is very strong, but once it fails, it's done. There's no backup. There's not a second trunk applied to it, unless you're one of these clonal trees out in Colorado or something. But that is fault resistance. The tree is designed to withstand any force that can be thrown at it. And if an outlier comes along and is able to overcome it, you're done. The other method is what's called fault tolerance, and that's like leaves on a tree. If you go out and pluck a bunch of leaves on a tree or even take off a few limbs, the tree can still continue because it has alternates. It's got redundancy built in, and it can keep going. Um, So, when it comes to fault tolerance, let's take a look at the Boeing 777, one of the last really, really great products that Boeing designed before they started having some of the endemic issues that we'll go into in a few minutes. But they have multiple engines. That's fault tolerance. If one engine fails, the other one can keep going and get you back home safely. Modern aircraft are designed in such a way that there is no point from gate to gate, from departure to arrival, that a single engine can fail, and that the other engine does not provide sufficient power to get you back on the ground safely in one piece. About a year ago, a Lufthansa flight at the worst possible moment on an A320, a little EU regional flight, had an engine blow up at the exact worst possible point, and the passengers went through the ordeal of having to go back to the airport and deal with a bus and get another plane before they continued on with their destination. That was their day. Fly-by-wire is a really great technology. That's where instead of when you steer the aircraft or control it, instead of having a single cable that's connected to the stick that moves the flaps, it's actually a computer sending digital signals to the mechanisms that control the surfaces, which means that you can route multiple paths of these cables. So if one gets severed, you have two or three others available to go. You have multiple computers. This is one of the really, really, this is one of those systems that not only improved efficiency, but improved safety as well. And then you have to have redundant sensors as well. If your safety is dependent on knowing exactly what your airspeed or your altitude is, you are absolutely not going to have one sensor, because if it breaks, you're in big trouble. You're likely to not even have two. You might have three, which was one of the issues with the 737 MAX, was that it was actually losing two at a time instead of just or it was essentially it couldn't read the second backup one if the first one failed. Now, for fault acceptance, you have things like the wings, the landing gear, and on a helicopter part that's called the Jesus nut. And this is where you don't have an option for redundancy. You must over-engineer it. You must look at every. There is no such thing as an outlier when it comes to the force for these. If it has happened before, you must design to accept that stress, whether it's clear air turbulence, um, some kind of rotational forces on a helicopter. And if you see what every aircraft is required to do that flies in the U.S., but Boeing has this really great video of it. The Boeing 777 wing test. The wing was designed to take 150% of the highest known observed load that an aircraft has seen on its wings, and it had to flex 150% past the deflection point that load would produce. Uh, it made it to 150%, and then they kept going because they wanted to see where it would break. If you have the ability to test to destruction, you always should do so, because you don't know your limit until you have reached it. And that's what they did. They tested this to destruction. It created a shock wave. It broke everything in the hangar, but that was on purpose. And it proved that this wing was ready to take whatever could be thrown at it that at least had been seen up until that point. And at that point, they had almost a century of experience with what airplanes had to go through. This we won't watch the video, but it's a great one. Um, so part of what drives aviation safety and so many other things, whether it's computers or medical, and this was discussed with, I believe, with insurance and reinsurance, is what's called the Swiss cheese safety model. It is, which is critical. You assume that parts will fail. They're going to. One way or another, something's going to break. And the design and the organization of your system, whether it's human systems for air traffic controllers, the way that a pilot and a co-pilot interacts, the computer systems, the engines, the hydraulics, even the doors. You have to have different layers so that when one thing breaks, there is another part or a component or a program or something that catches that fault before it propagates to a fatal result. Um, and you have to, so obviously you don't design components to fail. These aren't sacrificial parts. There are a few parts on an aircraft that are actually designed to break, and when they do break, that's actually, a light comes on as a warning sign, but those are the exception. But you need to build a system where failure is accounted for in every single possible component from day zero. And each layer of the Swiss cheese, has holes in it, but the next layer doesn't have a hole that's lined up. In the area where there has been a lot of focus on this over the past decade to two, has been what's called human factors, which is how people operate within the system. So here's a great picture of the Swiss cheese model. If it looks like it came from Wikipedia, it's because it did. But each of these red lines is a hazard. Each of the slice of Swiss cheese is a layer of protection. And in this case, there are only three layers. And one thing gets through, but in general, the layers are either more robust or you have more of them in there. So we're going to talk about an example that happened about 4 years ago on a United flight out of Denver going to Hawaii. Boeing 777, fantastic aircraft, and it suffered an engine failure. You can see, I'm not sure if you can see my mouse, but right here, it lost a blade on one of the engines. That's not great. These things are traveling, sometimes these tips are going faster than the speed of sound. Um, and this isn't like a diesel engine with a big heavy block on it. If something comes loose, it's going to, it can do damage. And as you can see right right here, this is actually lubricant oil that was on fire, not the full engine itself. So this is one of those situations that looks incredibly scary. The plane turned around and had to go back to Denver and they had to get a new one so everyone could continue on their vacation to Hawaii. But the engine failure was contained. That's the key word here. So the engines on the Boeing 777 were designed from day one to withstand losing an engine blade inside them. So if it got flung off from the base, it was designed to contain that the same way, the Kevlar and a bulletproof vest is designed, to stop a bullet. It's not going to be great, but it's not going to go pierce through. The engine covering was designed that if there was a loose blade in there, it would allow it to pass through and fall out. The 777 was designed from the get-go to have engine out capability, which means that if you lose one of the engines, the other one is going to get you back home safely. And the engines on some of these models are rated to cover almost 6 hours of flying on a single engine in case you're over the Pacific and you have to, travel 1,000 miles or more to get to an airport. And then the crew and the flight deck and the flight attendants as well are all trained for almost exactly situations like this. There's a checklist they go through line by line. There is an order of operations and how they communicate with each other. But it's a little bit flexible, so the co-pilot isn't locked into the pilot's authority. If the co-pilot sees an issue, they have the authority and the capability to raise that issue, to say we need, or my readings are saying this, we need to do that. And unfortunately, the system came about through incidences where planes crashed because there wasn't good training or the dynamic between the crew was not healthy or productive. But in this case, it worked very well. The A380 suffered two contained engine failures, or sorry, uncontained engine failures. So this is where something happened on the engine beyond what they had seen before and what was designed for, where a fan blade came loose and pierced the engine covering. And as you can see, um, in the slide, this Qantas flight lost the back half of the covering, and the Air France flight lost the whole front of the engine, which they were luckily able to find in the ice in Greenland. To analyze and figure out what the problem was. Keep in mind that despite the fact that these are the same model aircraft, these are completely different engine designs from different manufacturers. But again, there was redundancy. When the blade pierced the wing of the Air France flight, it did not sever any critical systems. Everything that it severed was either a non-critical system, or there was a backup that was able to take those to reroute the critical path. And both planes made a safe landing, and both of them were returned to service, and you might still be able to fly in one of them. The 2018 fatality that we discussed earlier in the presentation was on a Southwest flight, and this unfortunately was caused by, again, an engine failure where one of the blades broke off in flight, ending the 9-year safety streak of the U.S. And this was in a CFM56 engine, the most built jet engine in the world. It's around everywhere. Everyone in this group has flown on one. Um, However, in this particular case, it was an older engine design, and the maintenance did not detect fatigue that was inside the engine. This was one of those events that potentially prevented several other events down the road because they realized they had to be more aggressive about inspecting for this kind of damage and then rectifying it. And in this case, the engine was not designed to contain a blade failure. The blade left the engine and went through the window, striking a passenger, leading to a fatality. A similar instance had happened a year before on another Southwest flight with the same kind of engine, but luckily it only ended up in depressurization and a diversion, I think, to Trenton. So maybe ending up in New Jersey, maybe that you want to count that as a um, special kind of accident, but no injuries. So it is critical, absolutely critical when people are working on systems, whether it's aerospace, medicine, or anything like that, my specialty being aerospace, to look at what has led to accidents and incidences in the years leading up to the beginning of your work and learn the lessons from them, because all of these accidents have had very thorough investigations. Some of them have been multi-year efforts, and some of them have even revealed almost new types of science. The most famous is the de Havilland Comet, where this is what really drove research and understanding of metal fatigue and cycles. And this happened because they're on the upper side of the airplane, there was a little window that had square corners and not round ones. This is why you don't see square windows on aircraft. The pressurization caused a buildup of fatigue in the metal around this window, causing it to crack, and they lost two aircraft the same exact way under mysterious circumstances. And they actually built a swimming pool the size of this airplane and to pressurize it in until it failed to figure out what was going on. The DC-10 revealed that if you have a system that is critical to the safe operation of a flight, you cannot have a single non-redundant path. And in this case, there were doors coming, cargo doors separating in flight, severing hydraulic control lines for the engines and all the control surfaces on the back end of the aircraft. And losing one was enough to lose control of the whole airplane. There's a very famous video of a crash landing in Sioux City. It happened to a Turkish air flight very shortly after the type was introduced in the passenger service. And this is what largely drove what's called the fly-by-wire system, where if a door rips off and severs your control line, there's one next to it, two more on the other side, one in the ceiling, things like that. Um, Human factors and fault tolerance was really the fourth generation of aircraft. That's where a lot of work went into that. The flight deck of the Boeing 777 was designed with pilot input. Boeing went to pilots and said, hey, what do you hate about your job? What makes your life difficult? in the flight deck with the gauges and the dials and the controls, and they designed it around usability, the ergonomics. What's going to be in store for the fifth generation of aircraft? This is a question that's still open because neither Boeing nor Airbus has decided to take the step into that next generation. They're just kind of reheating older um, designs, putting them back in the oven. But some of it might be the approval and testing process because, as we learned with the 737 MAX, that was not sufficient to detect a fault before it entered passenger service. So, on the topic of the 737 MAX, there was a huge amount of testing done on the airplane, but it wasn't being done right and it wasn't being done smart. There was a major flaw in the design and it was getting through in the testing. Lessons from previous accidents were ignored. The MD-11, the successor to the MD-10, had a system on board that relaxed the stability for fuel efficiency, but led to two crashes because it did not behave as it should have on two different cargo flights on landing, causing the plane to flip over. So Boeing knew that if you had a stability augmentation system on board, you had to account for possible accidents, and that was not followed. Human factors were ignored. The pilots on board the 737 did not know that there was a stability augmentation system on board for the trim. It was not mentioned in the manual anywhere. And when the thing did start going into these runaway conditions, the crew were immediately overworked. So the crew did not have the energy to manage the situation. In both cases, the crash was essentially guaranteed. And Boeing did not train them and tell them, like, hey, if you've got a stabilizer trim issue, you need to press this button to disengage the system. Another thing was, and this is kind of sad, is that there was an insufficient response to the first crash. And the reason why was because it was Lion Air. Lion Air had already at that point a crash or two under their belts on other versions of their aircraft. And they were generally seen as not a safe airline, one to be avoided. There had been times where their certificate was put on hold, I think, or they weren't allowed to fly into certain countries because they weren't maintaining their aircraft correctly. And their crash did come about because there was a maintenance issue that led to that problem. So if the maintenance issue had been fixed, that would have been the layer of Swiss cheese to stop it. But the fact is that when everyone woke up and heard that there had been a Lion Air crash, a lot of us were just like, well, it was going to happen. Um, if it had been another operator, that might not have happened. And honestly, that's not an okay reaction from anyone to have blown that off, but it was part of the issue. So how did this happen? In this particular case, we're going to talk about the Alaska airline flight about a year or two ago where the door blew out and someone lost their cell phone. Um, very lucky there were no fatalities. It turns out that there were no fatalities because the person sitting in that seat missed their flight, missed the connection. But Boeing was outsourcing responsibility and quality control to an aviation system based out of Wichita, Kansas. Uh, so that was the first layer of Swiss cheese that was penetrated. There was not the proper oversight for the QC for this. The second layer was the technician failed to install the bolts on the door. So even though the quality control for this door wasn't great, had the technician installed all of the bolts correctly, it would not have led to a failure. It would have remained in place. But that did not happen. The bolts were improperly installed. I believe some might even been missing. And the final layer of Swiss cheese that this fault pierced was the inspection. Every time you do maintenance work, especially in something like this, you have someone else inspect it, and the inspector did not detect that the bolts were installed incorrectly. That is a major, major lapse. I worked at Delta doing in their engineering department for 3 years, and every time we had a work order done, the engineer had to sign off on it with their name. That's a level of accountability. A technician had to install it, sign off on it with their name, and then an inspector had to come in, a different one come in, and we did catch things that had been uninstalled correctly or design work that needed to be revised to meet our standards. But it was always caught because we had these multiple layers and we adhered to them. So here's a little bit of a summary of how long it takes for planes to crash for their very first time when a new model enters into service. And as we take a look, I have two of them highlighted in red because there are two very good aircraft with very good designs that since the last Risk Institute, I have had to update this with they have never had a crash to now they have. And that's the A350, which had the accident in Tokyo where a Coast Guard aircraft that was taking relief to a hurricane entered the runway by accident. They thought they had permission to go onto the runway to take off. They did not. They didn't realize that this flight was about to land on top of them. And unfortunately, led to fatalities on board that aircraft. I believe the Japan Air flights had no fatalities. There were some injuries, but everyone on board survived. But it took 9 years for an A350 to have their first accident like that. That is a very good record, especially when you take a look at some of these other aircraft on there, like the 737 MAX barely made it a year before the problem was revealed. Um, the 747 had some somewhat early on, but again, when you look at the reasons behind these, they're really only three design flaws in there, and one of them, the aircraft was the A320. It was pilot error compounded by a software design issue. That was something that was found out and immediately rectified, and this was a kind of outlier air show flight. But it illustrates the point that human factors really are the thing that are driving safety. And as a society, we have gotten good at them. We're getting better, and we're going to keep getting better. So to summarize some of the 737 MAX issues was serious design deficiencies, as we saw, because they lost one sensor, but the computer thought it was two sensors that were gone. The MD-11 taught them that you need to have really robust stability control systems if you're going to relax the stability of the aircraft. A320 showed that pilot software interaction needs to be really, really robust. And the 737's been around since the 1960s. This was the fourth major redesign of some of the components on board, and they really were pushing the limit of what they could do with this airframe to bring it into the modern era. And they got a lot of things right, but this was one of the things where they were biting off more than they could chew. And there's an endemic issue at the company. We have Starliner here, which is very probably going to be the first spacecraft to ever take humans to space, but not bring them back. This thing is still not considered operational after about 6 years after its first test flight. Every flight they have done has had major issues, and the entire propulsion section is being redesigned currently as a result of this. You have the 777X, the next generation of the 777, which is a great airplane, but again, they have so many endemic issues, and it's with the management largely, that this thing first flew in like 2017, I want to say, and not a single one has entered passenger service yet. They're still testing and tuning the design. And then, of course, you have the door. And a lot of people ask how this came about. It was largely because there were two companies in America that were driving the commercial aviation market. You had McDonnell Douglas and you had Boeing. And Boeing was an engineering company run by engineers, tackling looking for problems and tackling them. And then you had McDonnell Douglas, which was a business that happened to be building airplanes. And they decided to merge so that Boeing can grow their business base, get some of the military technology, things like that. But unfortunately, when they merged, while Boeing was the surviving entity, McDonnell Douglas's management stayed on board. And those issues perpetuated after the merger. One of the most symbolic well-known things was that Boeing was based in Seattle. So what did they do? They moved their headquarters to Chicago, a city that where did that idea even come from? And now a lot of people in the industry see Boeing as a stock company that happens to build airplanes. So, quick summary. The key to robustness of a system, the mimic, aircraft themselves are not anti-fragile, but the system we're able to somewhat simulate and mimic the anti-fragility we see in nature by increasing the robustness and finding flaws and using them to make the next generation, the next flight safer. So, learning how to contain errors and learning how to route around errors is critical. Lessons from the past must be remembered. That is the number one thing that drives improvement. Non-redundant parts must be over-engineered, and there's no such thing as an outlier if an aircraft has experienced that issue before and needs to be accounted for. Rigorous testing, training for the crew for every situation that you can think of. And that doesn't mean they have to memorize everything, but it means that they have to have a mentality and a system for when something goes wrong, they know what to begin to do. They're checklists because there are more problems than anyone can remember, but being able to default to the checklist and going down it line by line, that has turned countless flights with small situations that could have turned really bad really quickly, or flights with big situations that did turn bad into another safe landing. And then you have to have responsiveness and cooperative in the regulatory environment as well. This is one of those things where regulation has really, really improved the system because the regulations focus on safety rather than, telling airlines how much they have to charge for what market and such. They also don't really do part of it's also avoiding witch hunt or unfair punishments or looking for scapegoats. If you have done your job in good faith, per the book, you've done everything right and something fails, you are not held responsible for an incident because you were doing everything essentially as perfectly as you could. They look for what was the failure in the system that led someone who was competent and doing their job in good faith to the best of their abilities to produce something that allowed that failure to happen. Airlines are very good in the US of what's doing called the self-disclosure. If they find a fault, they report it to the FAA, and the FAA, instead of coming along saying, hey, we're going to take someone to jail or fine you, it's, hey, how did this happen? So we can prevent it for the next time. There was an issue about 15 years ago where every single MD-88 in the country, except for two, had a wiring fault from a repair published by the FAA. The FAA didn't fine Delta and American Airlines for having uncompliant airplanes. They fixed the wording and the instructions of the repair so that when the work was done in the future, it was done right. So here's a new slide as well. We're about to finish up as well with the slides, but consequences of human factors in 2025. We had the Delta connection flight that flipped on landing in Toronto. Luckily, everyone survived in that case, but it was pilot error, inexperienced pilots, and challenging conditions. We have the really, really tragic incident that happened in DC where the passenger plane collided with the military helicopter. There was major helicopter pilot error there, incredibly unsafe routing. Even if things were going perfectly, the path that helicopters were supposed to take was unacceptably close to the path that aircraft were allowed to take. And no one thought to just say, hey, if we're using this runway, helicopters shouldn't be flying here at this time. And then it was an air traffic control failure because they only had one person working the airport and they did not have the tools necessary to avoid this known problem. There had been traffic avoidance warnings at this airport multiple times. The same situation had appeared many times before and luckily did not appear in a crash or did not result in a crash, but it was a known problem. And then we have the Air India flight that happened just over 30 days ago where the fuel cutoff switch was moved from on to off. This is essentially like turning off the engine of your car while doing, 80 miles per hour on the highway. And this one, we don't really know what happened yet, why this happened. It is very likely a human factor. I personally do not know if this could have been caused by a software or mechanical error on the 787. I don't know how much control the 787 has over its fuel cutoff switches, but in general, Boeing lets the pilots have more control than Airbus does on these systems. So it is very likely, I won't say anything with certainty, but it is very likely that one of the pilots on board flipped those two switches that shut off the engines leading to the crash. And whether or not that was an accident, incompetence, or, and this is a very, very uncomfortable cause that has happened in the past several times, that was an intentional cutoff by one of the pilots. There have been crashes caused by pilots on purpose, unfortunately. And I'm not talking about terrorism, individual pilots. And on that jovial note, that concludes the slideshow aspect of it. I'm going to start taking questions. I will be in the afternoon session to start answering questions as well. So if we don't get to you, don't worry, I will be here. And if you don't have a chance to answer today, or you have a bad microphone and it makes your voice sound bad and you don't want to speak, feel free to find me at LinkedIn here. Put the link down below. And with that, I'm going to go directly into questions. Patrick, it looks like you had your hand up first.
Hey, Alexander. Alexander, thank you so much. I've been a recreational airplane and helicopter pilot for 15 years and in the process of becoming a flight instructor. This is one of my favorite topics. I could talk about this all day with you. But my question is, and you touched on it briefly, the automation management. In my most recent check ride with an FAA examiner, there was a heavy emphasis on um, being able to operate the aircraft when the automation fails, because it seems like we've reached a point where maybe we're over automating certain things, and essentially like the pilots are becoming too reliant on the automation, and when that automation fails, they just don't know what to do. And I'm pretty sure that was listed as a contributing factor in the ASEAN Airlines crash in San Francisco that you mentioned earlier in the presentation. So
Mhm.
I'm curious, from an engineering standpoint, is there any research into sort of like where the sweet spot is on that automation? Or from the engineering perspective, you're going to automate as much as you can and rely on the operational and the training side of things to just make sure that the pilots get the necessary training to be able to operate the aircraft when the automation fails? Thanks.
Mhm. That's a fantastic question. So when it comes to the design of aircraft, essentially what it is that when it comes to the flight deck or the procedures between the flight crew, uh, automation is there largely to allow the pilots to focus on flying first and foremost, if that makes sense. The It's not there to do everything for them. It is there to allow them to focus on doing what they do best, which is flying the airplane, talking with air traffic control. Um, and there are certain aspects where automation has, like, such as engine control. You don't want the pilots to have to be flying the aircraft, but then monitoring every single engine parameter when those can be done with very simple digital algorithms. And that's was one of the first things that was automated with computers in the 60s and 70s was engine control. But these aircraft are designed in such a way that even though everything is automated, the pilots have the final say as well. Almost everything has an option to be overruled by the pilot. Additionally, when it comes to the operational and trading side of things, pilots they've had to make two different sets of rules, and one of them is that there is a minimum number of takeoff and landings and flights that a pilot can do on um, using the automatic system, so that they get the experience, so that they're continuously doing stuff manually to keep their training fresh. On the other side of the coin is that there's a minimum number of flight segments that they need to do with the automation, so that they are trained and used to the automated systems controlling the aircraft as well. So there is a sweet spot, and it's one of those things where there's always fine tuning going on, but the manufacturers, especially these days, have a pretty good idea of where that sweet spot is. And I know that Airbus actually had to pull back a little bit and allow pilots to have options to override a little bit more of the automation that they initially had it intended. And unfortunately, Boeing tried to add a little bit more automation, but as we discussed in the slides, didn't do so in the best manner. Does that answer the question?
Yeah, I think so.
Mm,
Definitely from the engineering perspective, I think
mm,
for a little while, like you could tell, like
mm,
the lawyers got involved because there was a
mm,
perception that like the automation was safer, and so it was like use the automation as much as possible.
mm,
And then after a couple of these high profile crashes, um, like on the operational side, it was like, oh no, like that's when we saw the
mm,
like minimum hand flying and manual
mm,
operation of the systems requirements start kicking in. Um, but I wasn't sure, like from the engineering perspective, if they
Mhm.
thought they had found that sweet spot, which you seem
Mhm.
to indicate that they think they have, or they were continuing down the more automation path. So thank you.
Yeah,
Appreciate
it's there's every time they design aircraft, more and more things get automated, but a lot of it is more like non-critical optimization for efficiency things, like like maybe the air conditioning or when the certain lights come on, and things like that. But there have been, commercial aircraft has been able to fly autonomously from takeoff to landing since about the 1950s or 60s. Um, the NASA or the predecessor to NASA demonstrated that capability on a DC-3, and I think in 1957 or so. So the automation of flying the actual aircraft has been around, but it's also different too because general aviation has completely different automation options as well as commercial flying. I know that in general aviation, it's somewhat been a problem where pilots are just turning on the autopilot in their Cessnas because they can. It's a very rudimentary one. Uh, Whereas, people flying a Piper J3, like one of those new versions of it, don't have that option, and they're wearing themselves out because they're on stick and rudder the whole time. Christopher, you were next.
Thank you so much for a wonderful presentation. I learned a lot. And safety obviously is very important. So, what we can learn from one of the safest industries on Earth is critical. I had a couple of questions real quick. One is about good faith and not being punitive if someone was acting in good faith. I'm just
Mhm.
curious, if there's situations where it wasn't intentional, but it was judged that someone wasn't acting in good faith. I'm curious, especially about the inspector who missed all those bolts being missing. And my second question is, one of the things that can be external to the plane, I think especially planes flying near Russia these days, is GPS spoofing. Yeah,
Mhm.
I'm curious what talk there has been in the aerospace industry about how to deal with that. Thanks.
Yeah, those are very good questions. So the first one, you're talking about where what happens when people aren't exactly acting in good faith. There have been examples of where punitive measures, oftentimes in civil suits, have come against people who have been acting in a maybe they thought that what they were doing was okay, but if in the investigation they found that you're acting criminal, like negligent, especially to a criminal level, you will be held accountable, and that has happened before in the past. In the case of the door coming off of the Alaska air flight, I don't actually know if they were able or what the determination was in terms of how that slipped through the cracks. It could have been the inspector didn't catch it because the documentation on how they were supposed to inspect that work was incomplete. It could have just been they did, what's called pencil whipping, which is just be like, oh, I'm supposed to do this and show that I did by signing off. So they just sign it without doing the work. Um, as for the GPS spoofing thing, that is a major issue, as we saw with there are flights in Europe where they've had to turn around because they're trying to land in, in Tallinn or Latvia in the Baltic states, and Russia's been doing spoofing in the area, and they don't have the accuracy they need to land in low visibility conditions. Um, and probably the best workaround to that is to just rely on more traditional navigation techniques. So the traditional instrument landing systems, the radio beacons, and things like that, because I'm not sure if Russia has targeted those. I know that they do GPS, but it is a concern and it's something that the industry has been talking about and taking seriously. I don't know what steps have been taken maybe in the past year or two where they've become more aware about it, but that's something I'm going to take a look at. Maybe in the afternoon session I'll have an answer.
I guess I
Um,
was real curious. How do you detect the GPS spoofing? Like you can switch to other ways of flying if you know you've been spoofed, but how do you know?
That's a good question. I actually don't know the answer to that. It could be that these pilots are because these aircraft, none of them rely solely on GPS for navigation. They because there are areas in the world that don't have like the GPS system installed for landing and takeoffs. So they have their traditional navigation using inertial navigation units and radio beacons and things like that. They all have those on board. In fact, there's some aircraft that don't even have the GPS option. So they might not even know it's happening, but I'm not sure what the procedure is for determining spoofing. Um, I have a suspicion that when Russia's doing it and they're doing it on purpose, these pilots, when they're locked into their GPS, figure out it's like, well, when they're trying to land in, Helsinki, they're not over, and it tells them they're over Miami. They probably know that there's an issue, but I'll take a look at that. It's a good question.
No, there's a
Luis,
you,
sorry.
sorry, you actually do get a warning as a pilot when your
Hmm.
inertial system disagrees. So
Mhm.
pilots can know pretty well in advance as
Oh,
soon as they
yes.
see it.
Yeah.
So it's not like you're flying blind, unless you intentionally ignore it and just trust your systems to just guide you all the way to the airport, and then you suddenly
Yes.
wake up. That's
Which is
great.
it's a human factors issue because there have actually been accidents where pilots have ignored navigational warnings because they thought that the warning was incorrect, was an errant one. So before the next question, I will make a side comment that if your question is more about general aerospace, space flight, rocketry, I actually currently work on designing rockets and launch vehicles as well. This doesn't need to just be limited to flying on your 737. Feel free to have a question that's a little bit more um, out there, as my background might indicate. So, Luis, you're next.
Oh, thank you, Alexander, for the presentation. So yeah, we've basically seen that this system learns from its mistakes, basically.
Mhm.
So I want to know exactly how it learns, right? So I don't know, or how do you make sure that it learns as a whole? And by that I mean, um, for instance, if after one accident they find that there was a design flaw or there was a part of the plane that uh, didn't work, or there was a problem with the system in the of the plane, or any other part. Are are those planes recalled, for instance, like and
Mhm.
then or how exactly does that happen? Are they does that immediately translate into all the worlds immediately applying and making sure everything is in compliance with that new uh, factor? That's
Yes, that's exactly what happens is that there's a notification system out there. They're called airworthiness directives. That's one of the stronger ones. There are also lower level ones that just say, hey, service bulletin, be aware, there might be an issue. And those are distributed to all of the operators of these aircraft, all the airlines, they're put out by the FAA with work from the manufacturers and the NTSB, the National Transportation Safety Board, when they're involved. The other safety organizations have means of doing so as well, but it's a notice system that say, hey, we have become aware of an issue, and it sometimes doesn't even come from a crash. It could just be, someone going through some old paperwork. It could be a pilot just complaining about it, and maintenance opened up a box and saw like, oh, well, these wires are a little bit more corroded than they should have been. So they'll put out a notification. And these operators will go in and see, like, hey, are we having these same problems as well? And if they are, they're going to inform the FAA or the EASA or the JAA, any of the appropriate authorities, and that information, when the system works, gets fed back to the safety investigators, the original manufacturers, and the other airlines as well. And there have actually been times where a crash investigation has been solved because the issue had appeared on other aircraft in an area where they weren't inspecting. And then they began to do inspections and saw that, oh, these all have them. And so we need to fix them. And so what they will do is they'll state, hey, you need to inspect this part. And if you inspect it and find that there's an issue, you have this many cycles or hours. So you can fly the plane maybe, 5 times, 10 times, 500, depending on the severity, what the part is, the implications and all that. Or you have to do it within a certain number of hours. It could be one, it could be both. Um, and they'll say this needs to be fixed within a certain amount of time. And there have been times where there has been an error that was considered so risky. They have said, as of this moment, no aircraft of this type can fly until it has been proven that this issue has not appeared on that particular airframe. So if you have 100 of them, that's a lot of inspections and a lot of work you have to do. And so that system is out there. There is already notices out there for airlines to follow if you have a 787 or any 787-like flight deck to make sure that your fuel cutoff switches are mechanically sound. because we now know that they were flipped on this Air India flight. They don't have any idea how it happened, but now that they know that that was part of the problem, people out there are checking, and maybe they'll reveal that there's some kind of mechanical flaw in the material they made it out of. It could be every single one in the world is perfectly sound and absolutely fantastic, and that's going to lead them down the path either way. Does that answer the question?
Yes, thank you so much.
All right, Jose, you were up next.
Hi, Alexander. Thank you for the presentation. I have a little bit of conceptual doubt because, yeah, I understand that all these risk mitigation measures that are implemented in the airplanes, the stream testing, lesson learned, redundancy in every critical component, all of them are making the plane robust. They are
Mhm.
making it more resilient to a number of incidents and conditions. But they have trouble to understand how it can become anti-fragile, as you were explaining in the very last slide. Is there any scenario, is there any control to make a plane gain in case of an incident, in case that it loses an engine? I understand that the industry may gain because there are less incidents, but I don't know if a specific plane can improve and become anti-fragile. I don't know if.
Yes, that happens all the time. So, like I mentioned, that airworthiness directive, sometimes that will come with a either a future or with the initial issuing a work that needs to be done on the airplane where a design change has been made and they are now incorporating it to make it better. So, every Boeing 747 was required to either be retired or have a special system on board that injected nitrogen into the fuel tank so that vapors could not combust because of TWA Flight 800 that happened back in 1996. So the Boeing 747, because of that accident, became safer. The de Havilland Comet continued to be built for another decade or two after those two bad accidents, and they were built with round windows. So they took the findings of these crashes and the particular aircraft that came afterwards were improved by these changes as well. But again, it's kind of a almost like a simulated anti-fragility because you have to be willing to do the work. It just doesn't happen magically. It's not like if I go outside and throw myself against the wall a few times, my bones are going to be stronger in a few weeks, depending on how hard I do it. You have to put in the work for it. Does that answer the question?
Yes, I will probably drop you a message to continue the discussion.
No,
But
yeah,
thank
absolutely.
you.
Yeah. Jamil, you were next.
Thanks, Alexander. This is a great presentation. My question was regarding some of the Boeing things that you discussed earlier. How, given sort of some of the systemic issues at Boeing and some of the things that have come out regarding, changing culture and things like that,
Mhm.
how should we think about it in terms of, connected things, accelerating some of the issues with planes that are out there? Is it limited to just the 737 or could be impacting other things? Like, does it make
Mhm.
overall air travel a little bit more unsafe, especially with Boeing?
So it puts the aircraft that they currently have operating out there at it can put them at risk if they are, especially if they are changing things, if they're making changes to working systems. So for example, the 737 next generation, which is now the previous generation that came before the Max, there were a couple of things where they incorporated changes from the Max airplanes as a retrofit on those. So that's where the management could be affecting a design of an airplane in a negative way that was already fairly safe. Um, Additionally, planes built of those older models in the current day have had some quality control issues. I believe a lot of those they've gotten under control now. Um, but the management, yeah, the management and the culture does have an impact out of just, oh well, our products are now late and overpriced, and it's affecting the other programs as well. Like I said, Boeing Starliner, their capsule for taking astronauts from Florida to the space station and back, does not take them from the space station and back. It's only taken them there. And that is that shows that the management, the top level management is percolating down into other programs as well, because those are two completely different business units. They shouldn't be having interconnected problems, but they are because of things that are happening at the top as well. Boeing's management might be making Airbus planes safer because they're now building more of them and they're flying them, and Airbus is probably looking at some of Boeing's issues and saying, "Hey, well, let's fix this before we get caught doing the same thing or using it. Let's say, okay, well, let's avoid this kind of technique as well." And these the Boeing issues are one of those things where we're now really aware of it, and some steps are being taken to rectify them. But there's no reason that they can't be taking more. They need to what they need to do is they need to start putting engineers in charge of the company again, if you ask me, or any other pilot or engineer, or even most of their employees out there. The 787 was one of those things where it was kind of designed at the end of their heyday of competency, but the beginning of their management issues, and they moved production to South Carolina. And for a while, airlines were refusing to take delivery of these aircraft built in South Carolina, where they built a factory to save money on labor costs. So they were flying them to Seattle to be redone by the more expensive labor force, costing the company billions. They're definitely in a save a penny, lose a dollar sort of rut. But cultural changes can be made. Once you are aware of a problem, they can be fixed. Delta Airlines recognized that they had some cultural issues back in the early 90s, and luckily it did not come to a head as a fatal accident, but they were afraid that it had the potential to, and they put in an active program to change the company's culture. And it paid off over the years, and it took years to do. It took a decade, maybe even two, until everything had cycled through. But it can be done. And the second you do it, you do start to see positive results when you enforce a culture of accountability, safety, and vigilance as well, because you don't vigilance being, the looking for problems, fixing them, but realizing sometimes it's not one person's fault. Sometimes it's just someone doing their job the best way in a system that needs tuning. Does
Yeah.
that answer the question?
Can I ask just a small follow-up? I
Mhm.
wonder, like, I understand, like, one of the things that concerns me about the Boeing part is that the 737 came to head
Mhm.
very quickly, initial,
Mhm.
life cycle early on. But could there have been lapses earlier in other airplanes, like sitting dormant, kind of like a turkey problem? You're like sitting
Mhm.
dormant, invisible, and all of a sudden, whatever the point is of breakage, because if there's been, corners cut on safety or
Mhm.
some kind of material reliability, all of a
Mhm.
sudden at a 7-year point, whatever the breaking point is for that material, for all these aircraft, it starts kind of showing up
Mhm.
after a period of time. That concerns. Can there be some
There,
kind of issues because of that?
there could be. I can't say that there aren't any, because this whole institute is about people finding things out the hard way after a long period of time because they didn't see any. But the best way around that is to build as many of the planes as you can, fly them as often as you can, and test them as thoroughly as you can. So anything that is lying and sitting around waiting, um, is discovered early on, in that testing phase, in the early days of operations, in a way where it could be fixed before something really bad happens. There have been a couple of crashes where there have been problems that have been laying in waiting for, sometimes over a decade, but those were times where the airplane had a deviation from the correct configuration. One of them was, I think on more than one occasion, but on one particular occasion, a bulkhead on a 747 blew out, causing the loss of the entire aircraft with everyone on board because it had not been prepared correctly. Or sorry, it had been damaged and not been repaired correctly. Had they followed the instructions to repair it, um, it never would have happened. There were other aircraft out there with the same repair that were totally fine, but it was done incorrectly, and I think it was like 10 years later that the plane crashed because of that damage. Um, so yes, it has happened. They've of course been, few and far between, very luckily. I will say that when it comes to Boeing aircraft, whenever I'm on a 757 or 67 or a 737 that isn't a MAX, I don't think about it twice. Because again, these are older designs, and as long as they're sticking to those designs when they build them and operate them, and the airlines do their own inspections as well to make sure that they're getting the design that they ordered. Um, there's a little bit of separation there that makes things a lot less scary. Like people say, "Oh, I'm afraid of flying on a Boeing 757." Don't make sense to me. Those things are built like tanks. They are incredible. All of them are old and they just keep going and going and going because they're just great airplanes. And Boeing used to build fantastic airplanes, the best in the world. Kunal, you're next.
Hi, Alexander. Thank you so much for the opportunity. My question is, even though the machine part of the airplanes it's getting better or it's robust, how do you deal with the human factor or someone who has an intention to do a mischief? Like, is there, like any thought to that stuff?
Yeah, so for the human factors thing, a lot of it is what they do is they'll take pilots and just put them in these professional, multi-million dollar simulators and just throw every issue they can at them to see where do the pilots break down as individuals in doing their job, or where do they break down as a team in their cohesion. And what they will do is they'll be like, okay, well, this is where it went wrong. Let's see. Okay, let's try this technique. Let's do it again. Do it over and over again. It's that practice and repetition that makes perfect. There are a lot of opportunities for engineers and airlines, regulators, teachers and things like that to go through that process and figure out where things are. And that's what, after an accident, what they'll do is they'll take pilots from, other airlines and put them in the simulator and recreate the accident and see how they respond and figure out, was there a correct response? Is there a wrong one? And if there is a correct one, they put it in the notebook. So if it happens again, the pilots just flip to, that page and go through the steps of how to get there safely. Ask for, bad actors. Of course, after 9/11, they secured, the flight deck doors and the locks and things like that. There have been, at least in Europe, after a really, really horrible tragedy where a German flight was crashed due to the actions of the pilots, they're doing a better job at making sure pilots are, physically, mentally healthy as well. Unfortunately, that was one of those crashes where there were a lot of red signs and some shortcuts or red flags, and there was one or two shortcuts taken. Um, as well. Those are a lot more difficult to prevent, obviously. But again, even with like the Malaysian airline flight, where that was almost certainly a pilot intending to take his own life, with the passengers as well. Obviously, people are now looking into more robust ways of finding those aircraft or detecting when something is wrong. Keegan, you're the next question.
Thanks so much, Alex. Appreciate the presentation. My question's about your comment on focusing on figuring out the problem in the system and not penalizing the individuals. How do we reconcile that approach with kind of the concept of skin in the game?
So I think that's completely compatible with skin in the game, if you ask me, because um, it's I mean, obviously what it is if you've done something wrong or you put people at risk, you're going to get penalized for it as well. But but if you make people feel like that no matter what they do, they're going to be penalized, even if they um do things wrong, you're going to get people feeling like, okay, well, I'm going to get in trouble anyway, so I'm not going to do it right, or they're just not going to participate in the system as well. Does that kind of make sense? Does that answer the question?
Yeah.
Yeah, it's I mean, obviously these people know that if they do something really bad, really wrong, or are negligent, even if they're unaware of it, they're going to be held accountable. So there's a degree of vigilance. And again, the people working with them are also vigilant of the work of the people around them as well. It's just that we're not, yeah, it's for skin in the game to work, you can't punish people for doing the right thing to the best of their capability. Um,
Right,
you
and the
can't
system
like,
breaking down.
yeah, exactly. Like, I mean, look at nuclear reactors, the difference between what you see in Western nuclear reactors, and if anyone's seen the TV show Chernobyl or read, any of the books about it or done the analysis of it, um, as well. That's a great example. All right, Ronnie, you're the next question up.
Yeah, thank you, Alexander. Pretty awesome presentation. I loved it.
Mhm.
Just a little point of view from me. I work in cybersecurity,
Mhm.
so I don't know much about planes and stuff. But I recently read that, for example, some Emirates like planes like the Airbus A380, they are trying to have like software updates on real time. I just wanted to know your thoughts about it, or if you know something, or is there even a reason for it?
Yeah, that's a really good question. Real-time software updates. I would say that if let's say I was a CEO of an airline, I would definitely say that if you're going to update the software, it should be done manually. I know that for the 767 and 777, because those are computers from the mid 80s to early 90s, software updates are still distributed by Boeing on the floppy disk, not the 3.5 inch, like the floppy disks, things like that. There are probably some aircraft out there that use USB, but I think that because the architecture of these computers are not like, your laptop with Windows or anything like that, they're much more primitive software, so maybe they're a little bit more secure than, it's not like a Windows vulnerability is going to immediately affect the operating system of, the flight navigation computer because the architecture is so radically different. But I would be against over-the-air updates automatically, just so what software is on board your aircraft, the pilots are aware of it, and it's an additional level of isolation from a bad actor who might have access to that update or that data. Um,
Alexander T, can you stop sharing your screen since you're not using it? Thanks.
mhm.
Thank
So,
you.
mhm. Does that answer the question?
Totally, totally does.
Yeah.
Well,
I
I'd just like to mention about, the over-the-air update. I have a Tesla Model X, which I love. It's a great car, but they update it over the air, right? And
mhm.
I'm sure they test it and everything else. But, about half of the time when they do that, I have to uh, I have to sort of like reboot the whole system, and check and then reset certain settings and all
Mhm.
this sort of thing. So I can imagine that with an aircraft, that's not the kind of model you want to follow.
Mhm. Yeah, exactly. Now, an over-the-air update to something like, like the entertainment system, like that's probably annoying and not the best way to do it, but I'm not going to lose any sleep over that. But yeah, exactly. Like the Tesla thing immediately comes to mind. Let's see. The next question is Mitt.
Yeah, Alexander, thank you very much for the very insightful presentation. My question was more in regards to the future of, I guess, air travel, and
Mhm.
is primarily in terms of supersonic flight. I was wondering if you had any opinions, data, or just banter about boom and some of the new supersonic technologies that people are using. And in addition to that, if you could elaborate on uh, maybe drone travel, I'm be curious to understand what your opinion is on it.
Yeah, so we get this question every time, and this morning as I was getting ready, it's like, I wonder how long it's going to take for the supersonic question to come up. So Boom, for context for everyone, Boom Technologies is a company based out of North Carolina and Colorado that is working on the next generation of supersonic transportation for passengers. Their aircraft is called Overture. They flew a subscale small test airplane about a year ago, and part of their design is the shape of the fuselage has been optimized to reduce sonic boom. Um, the so that it'll allow them to fly over land. You'll notice that most of the flights out there where flying supersonic is desirable are still over the ocean, and there's still no supersonic aircraft out there. And the thing about it is that you can build an engine that is great for subsonic travel. You can build an engine that is great for supersonic travel. It is the laws of physics largely preclude the ability to build an engine that can operate efficiently across both. And the thing is that you need to go through the subsonic air to get to the supersonic air. There's just no way around it. Boom has consistently iterated on their design, and every time that they have iterated and fine-tuned the design, the plane has gotten a little bit slower and a little bit smaller. The fact is that at the end of the day, the number one thing that drives people to air travel and picking who they're going to fly with is the price of the ticket. Sometimes the comfort of the seat and the amenities and the flexibility and the reputation. It is almost never the speed. There are very few people who need to be somewhere in 2.5 hours on the other side of the ocean. And this is frustrating for me to say because I would love to fly on an aircraft that's supersonic. The Concorde is one of my favorite airplanes. I have a little model here in case I need to do a visual representation of something. But the problem is that supersonic travel is going to be kind of like Ferraris. There's a market for it, but is it enough to sustain an entire business? And it's always going to be for people where money is disposable, but time isn't. And at that point, they're probably going to go with a private jet because the time savings of a flying on a supersonic airline versus a private jet when you can take off whenever you like are probably pretty minimal. Now, if they can develop some new secret technology that no one's ever heard of, that has where the cost of energy and fuel is a rounding error of the cost of operating the flight, maybe we'll see something. But at the end of the day, you can't go supersonic without burning a lot of fuel, and people would rather fly on something that's, they'd rather have more leg room at a lower cost. Juan, you're next.
Thanks for your presentation. I was just wondering if you have a breakdown of, so you showed, for example, the window thing, that I can't remember the name of the aircraft. It's just a first principle problem. I mean, obviously they didn't know that you had to round that up. But so what's the percentage of actual accidents that happen because of first principles like that? And what is the percentage of things that happen for, say, with materials? So not a negligent thing, but you'll something will fatigue and break at some point, but not because you just cut corners, but because you just didn't know.
So for things where you just didn't know, I'm going to say that right now, that is about as close to zero as you can imagine. I can't remember the last time that there was a material failure on board a commercial aircraft due to unknown properties of that material rather than a faulty design or parts weren't installed correctly or things of the sort. Especially because almost any structurally critical part on the aircraft is going to be going through a very, very rigorous inspection cycle. So we were at NASA a couple of months ago, and they were talking about carbon composites and things like that, where they actually don't fully know every single trait and detail about them. But what they'll do is to say, okay, well, the structural member can last 100,000 flights, and we know that because we intentionally introduced a fault into it and tested it to 400,000 times. Therefore, it will break, but just you're going to be replacing it before it gets to that life limited part. And that's what you want to do when you want to push the unknown so far out there that you have a margin of several times at minimum. Does that answer the question?
Yeah, thanks.
Mm-hmm. All right, Andre, the floor is yours.
I had lots of questions, but I'm going to ask just one, I think most relevant. So you're an engineer, I'm not, because I have no ethics. I'm just a software developer. But there's still basically most of the time, most of my work in design involves calling a trade-off between some form of safety or some risk versus additional costs that it would take to to avoid it, or to prevent it, or to substantially reduce its probability. How do you see this being done or should be done in aviation, or if you want, rockets?
Yeah, so for aviation, there's actually a acceptable failure rate in it, but it's so small, it's kind of hard to measure on an individual component level, and it's like I think it's like every billion flight passenger hours or something like that. And what you do is you design to that particular failure rate, and then you still make it redundant anyway. As for spacecraft, for rockets, you really want your reliability to be in the upper 90s. competitive. You expect your successful launch rate for your first flight, you should expect it to be 0%. Almost no one builds a rocket that works completely perfectly on the first flight. And if it does, it means you probably could have saved money by building it or spending less time. And because those are low risk, there's no one on board, you're flying it over a secure area. Um, um, there's been one very, very popular, noticeable exception making the news that seems to be getting in the way of flights in the Caribbean. The guy has a rocket launch pad in Texas. He also builds electric cars and has very public rants. But in general, spaceflight, the risk tolerance is much higher because you're actually not hurting anyone. It's or at least you shouldn't be. When the second you start putting people in the rocket, though, you actually have a completely different risk profile and standard that you have to design things to, and your margins get a lot wider. So, it's what it is you there's no like it's kind of like the leak rate on parts, whether it's a balloon, a gas tank on a car. There's no such thing as zero leak rate. What you do is you design it really robustly, and then you measure the leak rate that you do have. And by the time you've stacked up all of those things where you have a known rate, the losses are so small, and your reserve is so high that you wouldn't see that if everything goes within tolerance and within specification, you're not going to have an issue. You have reserves there. Does that answer the question?
Yeah, pretty much. Thank you.
All right, Joshua, you're next.
Okay, great. I think Trishank was first.
Go ahead, please.
Okay. So what is the maximum number of major airline companies for safety? So just from like a bigger macro question, maybe we do have the ultimate at the moment, which is, two major companies. But yeah, what is that?
That's a really good question. That's one that I've thought about before, but I don't have a informed analytical answer. Maybe someone's done the math out there. I think the thing is that if you look at the numbers, there's no, and you would decide to assign correlation where there's probably none, that answer is going to be two, because Airbus and Boeing have primarily been the duopoly for at this point 30 years now, and those have been the 30 safest years of the air travel. But again, they've also been the busiest and the one with the most passengers. I would I would like to see one more enter the market, and it's looking like China is about to very seriously attempt to enter that market. They buy a lot of planes these days, believe it or not, and they're looking to build their own. So I could see that duopoly being broken by them. Also on the regional side is now almost a monopoly with Embraer now that Bombardier's out of the aerospace business and their better products actually now Airbus products. But the number of manufacturers, as long as it's not one, I feel relatively comfortable. Part of why I'd like to see more is actually I think it'd be fun to see more airplanes out there. But again, actually, it's one of those things where having that commonality between the designs and the parts probably improves safety, because the second you have one part that's common to all those aircraft, even though as long as it's not a failure-prone part, for example, the flight deck layout between all Airbus is common, and the fact is that pilots are a lot more comfortable with that layout. There are no changes between all of them, and that has actually improved safety. Boeing has been doing some amount of that as well. So it's one of those things where you really want to optimize the commonality so that to reduce complexity and unknown factors, but you don't want to have single point failures as well. It's a complicated answer now that I think about it. But does that answer the question?
Yeah, I mean, just one of the great things from this talk for me was that the reason we have such safety in aerospace is because of the number of replicates that we've had from mostly two companies.
Yeah. So one thing that I should point out, we didn't really talk about this that much, and I should have maybe mentioned it during my slides. I'll make a note for next time for this, is that we haven't talked about engine manufacturers, and they're just as critical to the safety of the aircraft as anyone else. So now we talked about the engine design philosophy, but out there the players are, you've got Pratt& and Whitney, Rolls-Royce, General Electric, you have CFM, which is a consortium between GE and a company that's now part of Safran in France. And everything we've talked about applies to the engine manufacturers as well. They're a huge part of it as well. So it's more than just Boeing and Airbus. And the thing about it is that there are Boeing airplanes that only have Rolls-Royce engines. There are Airbus airplanes that only have General Electric engines. It's one of those things where there are Airbus planes out there that probably have more American-made parts on them than certain Boeing ones, depending on how things go. Trishang, you've been incredibly patient. You have the floor.
No, thanks, and nice seeing you again, Alexander. Thanks. A quick comment. Software updates, my bread and butter actually. So I'm glad someone brought it up. We happen to design something for automotives in case you're all interested. So the idea there is that even if you hack someone like Tesla, it shouldn't be a game over scenario. I'm really glad to hear that avionics is still using floppy, so that's some measure of safety. My question is a little bit okay. Did you work with Musk at all ever? At
No, I
point?
never worked with him directly. I was just an intern there during the summer when I was a student studying aerospace engineering. I've worked very close with people who have worked very close with him at other organizations, but my first day there just happened to be the day they successfully launched their first mission to the space station. So he was doing like a little meet and greet, say hello to everyone. One time, I think he was in the bathroom next to me too, as well, as I was on my way back to my desk getting coffee or something. Maybe one day, maybe one day I'll start a Twitter fight with him. We'll see.
That would be nice. What do you call? So I was curious. What is your assessment of his skills does he how much does he understand about space engineering?
So that's the thing about it is that I'll try since this is being recorded to be mindful of any future career prospects.
Yeah.
I will say the one strength he does have is that he, or at least he used to, does understand aerospace engineering. He does understand rockets and how they work and rocket architecture. Maybe he's not the best in the world, but he is very competent at that. There are some incredibly off-the-mark management decisions that have been made at his companies, including SpaceX, in my opinion, that I would never make if I was in his position. There have been some engineering choices where I question the validity of them. However, I don't know the assumptions that they made in terms of, with the science and the physics behind it. And I don't necessarily know, team members actually really change your technology as well. Like if you're trying to do something, if you're trying to do something basic and simple, and then the world expert on this complex system walks in and can do it in their sleep, of course you're going to go with them. And I don't know like what aces up the sleeve they have, but yes, he does understand rocket science. He did read the textbook on it, and there is a textbook on rocket science that if you read from beginning to end and understand it, you actually probably know more than a lot of other engineers in the industry. So I will concede that that one point about him. But Starship has some major design issues, and the fact that they have flown it 10 times now without a single complete success is actually beginning to get incredibly concerning to me. From an engineering standpoint, I understand it's still experimental. But the fact is that they're now flying it in ways where it's impacting people's everyday lives if they're traveling across the Caribbean, and for it to have failed 3 times in a row in almost the same manner without it actually being fixed is kind of strange. And I'm not saying that it's the same problem every single time, but it could be that they have developed a system more complicated than they have the ability to get under control in a timely manner. That's not to say that they won't get it under control. SLS, the NASA moon rocket, is an incredibly complicated rocket, probably more so, and it flew successfully on its first flight, but it also cost several times more, maybe even order of magnitude more, and took 20 years to develop. Where Starship, they're knocking one out every couple of weeks. But yeah, there's Falcon 9, on the other hand, is an absolutely fantastic launch vehicle. It is the best rocket that I think in spaceflight history. The best platform. I think it's better than Soyuz. It's better than Saturn V. So I will say that Falcon 9 is a fantastic product, but Starship, their big mega rocket, it's not being designed only to send people to Mars, but that ability is being included. That is that's a very interesting beast, and I have watched every single flight of it to see what happens.
I had no idea. Their marketing is so good. I wasn't even aware Starship was so problematic. Thanks.
Yeah, the thing about it is that their marketing for Falcon 9 is bad, if you ask me, because every time they launch Starship, all the headlines are Musk blows up another one of his rockets, which is true, but it'd be kind of like if, like it would be like, oh, like an engine at Boeing blew up that in a laboratory. What does that mean for Southwest Airlines? Absolutely nothing, you know. Arya, you had your hand up for a while.
And then we have to stop.
And then we have lunch. I'm getting hungry, so
I'll keep the question for this afternoon, Alexander. No worries.
Okay.
Okay, great. So we can resume at 2 p.m. You can resume at 2 p.m.
Mm-hmm.
And thank you very much, Mr. Alexander T, for this lecture. And see you for those who are interested in planes. I'm not too interested in planes, but we'll be there at 2 p.m. Thank you.
That's great. Thanks, guys.
All right, so we had a lot of very good questions earlier. Thank you, everyone. A lot of interesting things that we discussed, and being that we finished precisely at 12:04, it sounds like a good time to take some more questions.
May I ask a question, Alexander?
Yes.
So in one of your slides, you said that you you're kind of learning from previous accidents to improve the design and so on and so forth. And I found that a little bit, in contradiction with the idea of fat tail, that you cannot learn from historical data because the fat tail is, is basically unpredictable.
This is my department. You're talking the wrong department. His errors are not fat-tailed. A plane crashing is not fat-tailed. And let me use a metaphor that had been used before by Russ Roberts. If a plane crashes, kills 300 people, it's a really big tragedy. Fat-tailed is if it crashes and kills every single passenger who ever boarded any plane before. You see, a company going bankrupt is not fat-tailed.
I get it, yes.
Okay, but the financial crisis of 1982, where banks lost every penny ever made in the history of banking, the insurance debacle with the asbestos, where everything ever made in insurance were lost in one event, and of course the crisis 2007.
Understood.
Sorry to barge in. If you have fat-tailed question, you come to me. All right. This department is thin-tailed, but okay.
So Alexander, hi. So first, just the elephant in the room. I just see Nassim up and you down, and if I look at your eyes, just you are father and son, just in front of me. You look excellent. But my question is,
there is a resemblance. I don't know from
there is a resemblance. May not be random. Very good. So I've got a
maybe
girl.
it's random. You never know.
18 years old.
Our appearances are completely randomly generated, based off of the cellular rule, whatever it was for genetics.
Yeah, I've got an 18 years old daughter who has done many internships at NASA. Because I'm not sure if you're aware, but in Bermuda there is a NASA station, monitoring station that monitors the travels to the International Space Station and everything. So Bermuda really was at the center in the Atlantic of monitoring the stuff. But I wanted to have your view on engineering in general, aerospace engineering, and some of the issues we hear with NASA, like right now, kind of the federal government with kind of what they're thinking about the reduction of costs in terms of the future of what the guys are doing. So that was my first thing, that given that you are in the field, and where do you see space travel, hum uninhabited, habited space travel in the future? What's kind of the timeline when you design the space ships that you design?
Yeah, so I'll answer the second question first because it's a little bit faster to answer. But the time scale for when you design a spacecraft is always going to be in years. There's really no way around it. It really depends on the size and the complexity and how much rollover you have from previous projects. For example, we discussed SpaceX with their rocket, the Falcon 9, flying, and I said that how it was a fantastic rocket. It got its name because it's a Falcon rocket with 9 engines. There was a previous rocket called the Falcon 1, which was a Falcon rocket with 1 engine, and it was the same engine across both of them, with some upgrades and revisions, and the engine eventually went through a ship of Theseus process where the engine that they fly today on that model with that same name is completely different from the previous one, but it was through a stepwise process of improvements. But so you can really pull back on your time scale and how much money you need if you're able to use parts, systems, and solutions like that are off the shelf, and you can get it down to a 3 or 4 year time scale. But if you're starting from a clean piece of paper whatsoever, and you're using the bulk of your complex parts are starting from scratch, you're always going to have piece parts and things like that are off the shelf, like connections and fittings and seals and maybe some valves and maybe some computers and things like that. But you're talking 5 years, 10 years, 15. If the system is a NASA one with a lot of congressional interference, you might be looking at 15 or 20 years. Um, for some of the most complicated ones. And yeah, the simplest ones is going to take 3, and that's just for rockets. For satellites, it can take anywhere from a couple of years to maybe 10 years to develop it, depending on the kind of return on investment the satellite's going to get. If it's a science mission to a far-flung planet, there might be 15 years of work in it. Now, oftentimes on those, it's 10 years of laying the groundwork and doing studies to see if it's feasible, and then 5 years, 5 to 10 years of really intense work. And for to give not to give SpaceX as an example from everything, their Starlink satellites or internet satellites, because they're small. They are a cluster with many small, simpler, easier to operate satellites. Their design process for those is pretty quickly between upgrades and new versions of it, whereas for something like Hubble Space Telescope or a massive geostationary communication satellite where you have one that's responsible for all the bandwidth of a certain type of communication for an entire hemisphere, those are much more complicated. They take much longer. They're much more expensive, and the risk is higher. There have been times where people have put multi-billion-dollar payloads on a several $100 million rocket, and they almost made it off the property before the thing blew up. Huge losses, and that's kind of what's driven this decentralization, this de-risking of moving telecommunications back to low Earth orbit with smaller, cheaper satellites where you have to launch hundreds of them, but overall it's a more reliable, robust system, and it's at the end of the day cheaper, and it's easier to do upgrades because those satellites aren't designed for a 20-year lifespan. They're designed for 2 to 4. And so you know that in 4 years, you can replenish all of them with upgrades without having to take something out of service that you're still trying to pay off. For human spacecraft, of course, that always adds a lot more time as well because there's so many more tests you have to do, forms you have to be able to sign off on and verify, and for obviously very, very good reason. To go to the question about NASA, you were asking, what's in NASA's future and what are they working on and what can they do? Was that the question?
Yeah.
Yeah. So that is NASA is a massive organization. It's like asking, like, what's the Navy up to almost, or the Air Force? And the answer is a lot. Unfortunately, not as much as they were a couple of months ago because of congressional funding. But NASA does everything from operating the International Space Station, which at this point is probably going to be in orbit for about another 5 years, maybe a little bit more before they let it burn up in the Pacific to be replaced with a more nimble, smaller, probably commercially sourced space station. The same way they got rid of the space shuttle and started using Boeing and SpaceX because it was cheaper and more capable. It could fly or sorry, not more capable, but it could fly more often. It was better suited for what they were doing. The SpaceX taking the space shuttle to the space station just for taking up people and replenishing supplies was kind of like driving an 18-wheeler to work, when you could be doing it on a bicycle, sort of analogy. But NASA had been doing a huge number of science missions, not just, sending another rover to Mars or Dragonfly, which is which is one of the ones that did survive, where they're sending a helicopter to Titan, one of the moons of Saturn. But all of these different types of telescopes and observatories that are just here in orbit around the Earth, that had just as much potential maybe as Hubble, but without the big name because they're doing stuff like X-ray or UV or radio, and it doesn't really produce the pictures and use like the big mirror aperture as much. They have a huge number of Earth science programs, a massive number of them, because NASA, National Aeronautics and Space, Aero, that's air, that's here. They're studying the climate, the atmosphere, what's going on with the ozone, CO2 levels, and almost any kind of earth science that you can monitor from space, which is pretty much anything that affects anything larger than like an acre, a farm, a small farm, can be and is probably best observed from space. That is NASA's has their hand in, or did have a huge amount of that. So much like they were doing everything from soil subsidence in Houston to measuring ice levels at the poles. They have a satellite in Lagrange Point that can see the entire Western Hemisphere all at once for weather observation. And a lot of these are or will be on the chopping block. So that is an absolutely huge loss. A huge number of the aviation safety things that we talked about earlier was driven by NASA. NASA has developed a huge number of technologies. Fly-by-wire was something that NASA worked on before it ended up in the commercial aviation sector. There's almost any technology you find in a modern aircraft, whether it's a glider to an A380 with 500 people on board, has something that NASA has worked on or is working on or is looking to improve on board. They do so much more than just launching things up and launch. Actually, NASA doesn't even have aside from SLS, which they're launching once every 3 or 4 years, they don't have their own their own rockets. They go to other people and hire them to use their rocket to take their payloads where they need to be. The same way when you want to fly from New York to Atlanta, you don't buy an airplane, you buy a seat on one that's already going there. Or if you're incredibly wealthy, you can charter one just for yourself if you don't want anything else on there. But NASA's even taken rides on rockets where they're buying one small portion of the rocket, and anyone else who can afford a ticket on the rocket's big rack of electronics where they can pop out satellites who can afford the price tag, they get to go as well. So and you were asking what the future of space flight or space travel has.
Yeah, and aerospace engineering.
Yeah, so right now there's a really big push to make as much of the space technology out there reusable for launchers for rockets. A lot of people see, for very good reasons, fully expendable rockets as being a dead end technology. It's in the past. Very few people who are developing rocket technology are not looking at it in some meaningful way. That doesn't mean that they're making a lot of progress. The ESA is consistently in lockstep with SpaceX and their reusable technology with a 20-year lag. But I mean, China's doing it. Russia has done as much as they could with the resources that they have left over. Every commercial rocket builder is finding some way to reuse their rockets. So we're going to see more and more of that. Fewer and fewer rockets are going to get thrown away after a single use. And what people are going to try and probably chase down is how can they use the upper stage, that smaller part that makes it all the way to orbit? How can they reuse those? And that's a really challenging question, especially on a smaller scale, because those upper stages are designed to make it to orbit and nowhere else. They can burn up in the atmosphere, but they're not designed to have the weight and the heft and the robustness to survive hitting the atmosphere, getting hot, and then coming back down to ground. So there's some of that in the future. We're going to see more on the human space flight side of things, more and more. We're going to see the space station probably move into NASA buys a commercially available space station that other people have access to. We already see that a mission came back last night where it wasn't a NASA mission, it was a private company that was flying astronauts on the behalf of science agencies of other countries, like the UK, for example. I think Italy might have been in there too. The company's named Axiom. So instead of them having to go through NASA to send astronauts to the space station to do science, they hired a company based out of Florida to do it for them. We're going to see more of that. So the space station is likely going to be following a similar model when it gets replaced. NASA's trying really hard to go back to the moon, and one thing that was not cut was moon funding. Now, some of it was moved around in different phases in a way that raised a lot of eyebrows from people who know what it takes to get to the moon and what we should be doing to get there. Um, but um, I mean, I don't think it's a politically charged statement to say that the current administration will sometimes be a little bit more generous with projects they see as having some kind of nationalistic prestige. And there's no way to get about it. There's a certain amount of nationalistic prestige in sending people to the moon and having them come back safely. China wants to do it. India wants to do it. Russia says that they're going to try it again. They say a lot of things, but then in terms of just satellites and things like that, we're going to see more and more satellites that are very small satellites that can be expended after a relatively short amount of time, built cheaply, going into low Earth orbit where you don't have to deal with delay communication or communication delays and lag, which isn't acceptable for a lot of internet connections. So by moving it physically closer to the Earth and decentralizing communication infrastructure in space, you have really made it way more flexible and way more usable for the everyday person. And we went from about 4 years ago that if you wanted as a end user to use space-based communication infrastructure, you had to have a several $1,000 satellite phone that usually didn't work, to now people have internet on their canoes while going fishing because of Starlink. And Amazon is doing the same thing. OneWeb is doing the same thing as well. There's hundreds of other applications that we just don't know about because we people like us aren't the end user. It's usually some company providing that service as well. So we're going to see more and more of that. As for stuff like going to Mars, sending people to Mars, science missions out beyond the solar system, I think we're going to continue to see a steady pace. We're going to see an increase in other countries doing it. So the UAE has already sent stuff to Mars. India has already successfully sent things to Mars. China has. We're going to see more and more space capable countries doing things along those lines. I think Japan might step up and start doing more. The European Space Agency wants to do more and more things outside of just their RN rockets, sending stuff for direct TV and satellite radio. For people from Mars, it's one of those things where we were going to put people on Mars in 5 years since 1969. Who knows what's going to happen with that? I can safely say that the amount of resources necessary to colonize Mars are ones that we don't even have enough of here on Earth. And if we don't have it here, we're certainly not going to find it up there. But the way that I see humans on Mars is the same way I see humans at the South Pole, which is there's a small, very focused, productive research facility there that has episodes of self-autonomy, then episodes of being reliant on the outside world for resources, but one where a lot of work is being done. keep in mind that a rounding error of what happens in space is like billionaire vanity projects for tourism, especially because almost those are all suborbital at this point. Everything up there is up there to do a job. Whether it's for the government, it's for the military, or it's for a company. And if that satellite is no longer capable of doing the job it's sent up there to do, they will retire it or burn it up.
Thank you.
Yes, I appreciate taking the that's the 15-minute version of the 5-minute version of that question. Lance, you've had your hand up for a while.
Great, thanks, Alexander. Appreciated the talk. Most of my professional background is in oil and gas, so technology, heavy industry, operating in extreme environments, high consequence of failure. So I was struck by the Alaska door example. So this is a sort of a root cause failure analysis question. You showed, I think, 3 causes, and maybe this wasn't intended to be sort of exhaustive, but one of them was, a failure to install the bolts or tighten the bolts, and then a secondary failure associated with the inspection of that work. And there's a lot that goes into, in my experience, root cause analysis in the oil and gas industry. I'm curious what sort of tools are used in aviation. When I saw that example, for instance, it seems like there's another layer that's missing. Why did this technician not install the bolts, or why didn't he tighten them? Like, I would have thought that this analysis would have gone deeper, and maybe it does, and you didn't show it. But could you just describe sort of what techniques are used with Taproot, or I don't know.
So the reason why that I showed 3 reasons there is because when I pulled that picture off of Wikipedia, it had 3 layers on there, but there's obviously depending on the number of layers that are extant can be a function of interpretation. Do you consider each bolt to be one layer? Do you consider, each step in the instruction to be one? As for tools to ensure things, are you talking about like mechanical techniques, or are you talking about like systematic tools?
No, systematic tools like an approach or a process to root cause analysis. So I don't, and I should clarify, I don't mean like looking at each and every bolt. The reason I asked the question is because what we found happens is you can always say, like, there's always an easy answer, which is it's this guy's fault. Okay, maybe they get penalized, but you can always cite human error for pretty much anything. But there are often other pressures or conditions at play that result in humans behaving the way that they're behaving. And if you just stop at, well, this technician didn't tighten the bolt, you miss the underlying, there was pressure to get the work done because he had to get to the next plane. He's evaluated on the number of checklists he fills out instead of the actual number of bolt. There's all these things that can complicate things, and you don't get there unless you go to that deeper layer. And there are some tools that I think do a better job, others do a worse job of getting to that true root cause, and that's the sort of process or tool that I'm asking about. I don't know if
there's a huge number of those. So obviously, and in this case, this particular tool didn't work, but there's an inspection that you have to sign off on. So that door should have been properly inspected, and it wasn't. But that inspection is a written down stepped process where the inspector is not just looking around for whatever. There are certain key items that an inspector needs to be looking for, and going down a checklist and saying, yes, this has been done, that has been done. Yes, we have, the anti-vibration, wrapping around on the wires. The torque level was set on the wrench correctly and things like that. And then they sign off on it. Oftentimes on things like that door, that was actually one of the quirks about it was that from the passenger's point of view, it wasn't a door, it was just a normal wall. It's called a door plug. If they had, I don't know if they took closeout pictures, but I know that in space flight, when you seal a section for the final time before flight, you take pictures of it with a camera. They're called closeout pictures. So you can inspect them after the fact without having to open them up. And if something goes wrong down the line, you can look at them again and be like, oh, well, there was this in the picture, and we didn't realize that was a potential fault, or we did something wrong. At pretty much every aviation based outfit. I know that Delta had this. I know that SpaceX had this. Um, there's a system for people to raise safety concerns. So let's say that you're a technician working on tightening those bolts, and you know that you're going to be prone to error because of the pressure. They're telling you, hey, you've got to get 5 doors done in a day, and you're struggling, starting around door number 3 to get them done, and shortcuts have to be taken. There's a system where you enter in that concern, you put it could be anonymous, sometimes it is, sometimes it isn't, but there are ways to raise concerns in an official context with a paper trail. So if someone ignores it, it's now on record that someone raised that concern and ignored it. This isn't like the Challenger accident where they call up someone and there were all these things along the way where people were able to be like, well, it's like, that's not really a concern. And then they had to, go through that whole process and the investigation of being like, well, did you know about this? It wasn't really documented as cleanly as it should have been. Um, and of course, like anytime you work on an aircraft, you have to sign off that you did the work correctly, and oftentimes you have to like initial step by step. So if you just miss a step out of, it's an honest mistake, your initials might not be there, and that's going to raise a red flag when they're looking at it. Be like, okay, why was this missed? Like, did a page fall out of the book? There have literally been times where there have been planes that have been at risk because of badly formatted instructions. There's a
Alexander, I should say, so I don't mean to monopolize the time, but I was actually getting to a question of like a tool or a process for the actual incident investigation itself. So if you accept that a certain number of incidents are going to happen for whatever reason, it's like, do you go through like a taproot type process? There are some of these that are
there's a process called that's really popular with NASA and a lot of space companies. I don't know what the NTSB use, which is fault tree analysis, which is essentially you look at every part, even when you're designing it before it flies for the first time, and you sit down and say, if this part fails, what are the consequences? And that ranges from a delay of 5 minutes to take off, a programmatic delay of several years, to loss of mission with crew or loss of aircraft with all passengers on board, depending on the severity of it. So something like the bolts on the door, if they failed, they should have known in advance that if those bolts fail, the door coming off of the side of the plane was a physical possibility, and they maybe should have done something different about it. Now, one thing that further complicates this is that not only do you have Alaska Airlines and their inspectors, you have Boeing and their inspectors, but you have I think it was Pioneer Aviation Systems based out of Wichita who designed the door on the behalf of Boeing, and their engineers and processes and quality control as well. But yeah, fault tree analysis is a very, very common way. I'm sure the NTSB has multiple techniques because sometimes that information isn't available or it's been destroyed in the fire where the wreckage is.
Right.
Does that answer your question?
Yes, that goes some way to answering it. I appreciate it.
Yeah. All right, Ollie,
sorry for interrupting, but I have one comment about it.
Mm-hmm.
I read that part of the problem was the change design. Apparently, the doors used to open towards the inside, which means that when the plane took off, there's higher pressure inside than on the outside. So the door, even if there would be no screws or bolts or anything, the door would never dislodge. But that was less convenient. Because of it, it was more expensive because removing the door during maintenance took more time and was more expensive because of it. So they made it more efficient by allowing the door to be accessed from the outside. And that's really the main reason for the problem. So it's, yes, people made mistakes, but the design was changed to start with.
Yeah, so this is a great example because
if the design wouldn't have been changed, then even with people making mistakes, this would never have happened.
Yes. So what I will say in the defense of this particular type of door design, maybe this particular design was faulty, but remember, this is a door plug. It's not opening and closing ever. Once it's put in there, to open it, you have to unbolt it, and you can install a door in the future, and all passenger doors that can be opened in regular operations, open inward instead of outward, exactly for this reason. But this door was designed, or you can design windows and doors and things like that where the pressure would be forcing them outward, provided you're doing it with a very, very good, reasonable safety factor and margin on board. And every single aircraft has sections that are like that, down, or from the skin to certain types of access points as well. You just have to design for them correctly. And in this one, it could be that the design was correct, but I don't know every single detail of this particular incident. I believe it's technically, it might still be under the investigatory window. That's why I didn't have as much to say about Air India or the flight over the Potomac, because there are no official findings for those, or no official determinations, just official observations. Like that. But if they had made a door that could only be, or a door plug that only could be removed by pulling it inward, yes, that might have prevented it. However, the idea of having a plug that can be opened from the outside is not abnormal, because those bolts are designed to be so strong, which in this case failed.
The interesting thing here for me would be this is one example of a potential root cause, which is an engineering change without a robust. So I don't know if this is true, but I'm just reacting. This would be an engineering change without a robust management of change process, where you can have a perfectly designed component, but if the system in which it resides and the operators who have to use it aren't aware of the change, you can have disaster. So that would be an example of a potential root cause that would be highlighted in a good root cause failure analysis process. Thanks, and I'm done.
Yeah.
Sorry,
All right.
I want to add one more thing on the door, and shut up. The actual checking, like there's a leak from internal Boeing employee website, which I haven't seen it yet, an official report. I haven't seen any. But the discussion there was that so there's an assembly line, right? You have like 3, I think, or 5 planes, and you don't want to delay any. And they actually was an inspection. They found something else being faulty, and to fix that faulty thing, they had to delay the plane, and they had to actually open that door. And so the things were checked, but they had to remove the door, and now they're under pressure. And I think they used 3 different systems to track incidents during production, which is required again for quality assurance purposes. And I think the mess up was the removal of the door was recorded in one of the systems, but on the other. And so, as usual, the Swiss cheese model, multiple systems failed, sort of exactly at the right spot. So the whole thing ended up visible to us as consumers.
Yes.
So
sorry, the name of the company
design.
was Spirit Aerosystems. I just remember now. Yeah, and
Yes,
they do a lot with the fuselage of the 737. And before I get to Ali's question, I'll make the final comment on this, and that is, when you have a perfectly good system on board an aircraft, if you're a maintenance engineer, you are not allowed to open it up or do maintenance on it without some kind of explicit instruction or approval, because of incidents like these where someone opens up something that was perfectly good and then messes with it, changes its status, and puts into service in a degraded status rather than an improved one. It's like, imagine if you went out to your car, opened up the hood, and started taking parts out of your engine and putting them back together. It's probably not going to run correctly. So moving on, Ali, you've been very patient with your question.
Hi there, thanks. So I have a quick question. I think in the slides that you were showing, you were talking about, the last slide maybe, if we want to have anti-fragility, we need to ensure we have the right regulatory environment, something like that. Can you elaborate a little bit more specifically in the aerospace engineering? I guess.
Yeah, so a lot of it comes from the fact that the regulatory environment, as I mentioned multiple times, doesn't try to look for blame. It looks for causes. Of course, so eventually someone's going to probably be left holding some kind of bag, some kind of responsibility, especially like in the door situation where multiple processes failed, that got messed up. But a lot of it has to do with the fact that a healthy regulatory environment should be capturing when something goes wrong. You want a environment where the regulators are capturing the reasons why something went wrong and implementing corrective actions. Otherwise, you don't get that mimicry of anti-fragility where something bad happens, but in doing so, it reveals a potential weakness that could have happened yet again, or in greater numbers, or in a worse situation down the line. It can range anything from, oh, we realize that our we need to increase the margins and the strength of the landing gear. Maybe that's going to happen on the next generation of commuter jets after that hard landing in Toronto where the landing gear broke. Again, that's a single point system, and it didn't stand up to what happened. Now, of course, it was caused by pilot error initially, but maybe they need to capture a wider range of landing conditions due to pilot error in that design. We haven't had any 747s blow up due to the fumes from the fuel building up in the gas tanks since TWA Flight 800, because they were able to figure out the reason and then implement a fix across the entire future fleet. So it could be in adding new systems for safing and making things more secure. It could be in airworthiness directives where it's just, hey, this part can break, just now always be on the lookout for it. Because parts usually don't break instantly. Sometimes it takes years and years for them. And if you're expecting it every 6 weeks, you're going to catch that long before it gets to its critical phase. A lot of people don't realize that pretty much every airplane in the world has cracks in the metal somewhere, and a lot of them are just tracked. They're kept in a logbook, and then like, okay, check for cracks every couple of flights or months or years, because they know that it's not a critical thing, and that it's not going to just suddenly snap on the next time. It's from regular wear and tear. Does that answer the question?
Yes, it does. Thank you.
All right, Kendrick, you're up. You're on mute.
Sorry. Thank you, Alex. What are the after effects of Elon Musk threatening to stop using the Dragon spacecraft to take crew and cargo to the space station and for Pentagon projects? Also, how far off are we from exploiting the moon's resources?
So the primary effect of Elon Musk threatening to pull Dragon from the space station has been a lot of idiotic discourse online. I have a strong suspicion that that will be the extent of it. But we never know. We're dealing with an administration and an individual who are very changeable and opportunistic. I don't think that's a controversial thing to say. That's just how it is. But NASA needs the Dragon to get to and from the space station. There are people out there who have flown on Dragon as recently as yesterday, and will have several other organizations as well, besides Axiom, who have flown privately on Dragon. So they need to keep the program going. It's kind of the reason for, the existence of an entire branch of one of his companies. I'm not aware of any Pentagon uses for the Dragon. The Pentagon's very much just satellites without any people on board in space. I think they see humans in space as a liability, and they're leaving it mostly for commercial and scientific purposes. But we'll see. I mean, it's one of those two things where, you can never make a safe bet on what's going to happen next. I will say that Boeing is working to get Starliner up and running as an option to and from the space station yet again. So we'll see what happens there if they're able to get their ducks in a row and demonstrate that the spacecraft is safe and reliable enough to take people to and from. Because NASA, the reason why we have Boeing and SpaceX both providing the same service is specifically in case one of them has an accident or isn't reliable. There's a backup. You're not left stranded. It's diversification, very basic stuff. The question was how far we are from extracting resources on the moon. I think that we will have that shortly after we have cold fusion and flying cars. A lot of people just don't realize how much energy it takes to get to and from the moon in terms of chemical energy. And the moon doesn't have a lot up there that is useful down here. The only lunar resources I can see being useful is for um, any kind of space station like research outpost on the moon. So kind of similar to, like the South Pole or some of these underwater research facilities where people have lived for a couple of months, or like the space station where maybe they'll use, if there's ice on the moon, maybe they'll use that for making water and air to breathe. And there have been some research projects on using lunar regolith, moon dust, in 3D printers to make parts. So that's about it. But it's such, you can get stuff to the moon. Bringing it back is a whole layer of complication. Um, there was a comment made last week about investing in gold, and until they start extracting gold from asteroids, the value of gold is pretty safe. And I said that no one in their lifetime in this group has to worry about that, and I don't think any of our successors are going to. To put things in perspective, NASA's doing a sample return mission that's going to cost billions of dollars to bring back a few grams. So that is the cost of going out into the solar system, getting something from another celestial body and bringing it back. And I can't really think of anything that's several $billion a gram in value, except for maybe like antimatter or hyperpalladium or something like that. And we can probably make that here in the Large Hadron Collider. Does that answer the question?
Yes. It
Yes.
makes me wonder, in relative terms, when the European monarchies sent out explorers, how much did that cost relative to what we spend in space today? Was it similar or a lot
I
less?
I actually don't know how much the old monarchies of Europe spent on sending their ships and crews out across the planet, but that's a very good hypothetical question. I will also say this much. I hope I'm wrong. I hope that there is something useful on the moon that can be returned with some economic efficiency, because I think it would be absolutely fantastic. Blue Origin's long-term goal is to move a lot of industry into space where it makes sense. The former CEO of Google is recently took over a rocket company named Relativity, and their bit used to be we 3D print everything. Now their bit is we're going to be keeping data in space because we're using so much electricity for data storage and AI and stuff like that. And electricity in space is virtually free. Once you're up there with solar panels, they want to see if there's an economic case for moving computing power and storage into orbit to free up resources down here. Jorge, you had your hand raised?
Yes, a couple of questions interrelated. There's a dude called Chris Surdak who used to work in the Terra program for NASA, and he wrote a book called The Jerk. And The Jerk is about second moment effect. I mean, position, velocity, acceleration, jerk or jolt, and so on. And he sees second moment effect of things, not just the speed at which we do things, but the acceleration and the change in acceleration from a structural point of view. So my question, when you do this stuff like an Ishikawa fish analysis, say what is the root cause of something, there are two ways of doing that. One is saying, okay, if this fails, this fails, this fails, this fails in one direction, but then you do the other direction saying, if these fail for unknown cause, because I know all the reasons why this has failed in the past, but I don't know the reasons that I don't know about that it has not failed yet. So there's a propagation and back propagation in the Ishikawa thing. How is it being dealt with? Are you considering the things that you don't know in each of the parts, the chain effect from that point to one side, regardless of the possible other causes that you already know may have created that?
So if you're doing fault analysis on a new design, in general, you will you should be ignoring what could cause it to fail and just what happens if it does fail. You will not, but you will do. So what you'll do is, let's say you have, for example, I worked on the ignition system for the BE4 engine as deployed on ULA Vulcan, and the ignition system was one of those things where did the analysis that what if the spark fails We didn't say how is it going to fail, but what if it did? Now, we do look at how will other parts fail because of that, but when you're doing the analysis on those parts for if they fail, you're not going to be like, well, it can only fail if this part upstream fails. You're looking at you should be. Now, people might make that mistake because they haven't gone to this institute and learned from very smart people like you and I, but or smart people like you especially, maybe not me. But you should be looking more at what happens if this fails rather than what could cause it, because again, you just can't think of everything. Now, I was very lucky that because this was the ignition system, if it failed, it just meant the thing didn't turn on. So it was quite possibly the most benign part of the system. It was just like, oh, it didn't turn on, try again tomorrow sort of system. But something like the, let's say the launch escape system on a capsule with people on board, if that fails, you have lost the crew. They're dead. So you you really want to be a lot more rigorous with something like that. Does that answer the question?
Yes, the reason of the question or the motivation of the question is that when you design something to be reliable or resilient, you usually analyze how do I cover the loss of functionality in something regardless of the cost. So for example, in a city, you're trying to build resilience to terrorist attack. You don't know what that kind of attack is going to be, but maybe you lost the access to a building, okay, or you lost the exit to a building, or you cannot evacuate, or you cannot evacuate a building. So you say, what is my reaction to something failing, regardless of the cause of failing, and you capture things that may have caused a similar effect without you knowing that that was a particular cause.
Yeah, and the door of a building is a very good example of something on passenger aircraft. They are designed to be evacuated in the required amount of time with only a fraction of the doors, specifically because you don't know what might cause a door to not open. Does it affect the entire side of the airplane? Is it just that door? And that's why there are doors on both sides and they're spread throughout. And you can only have a certain number of people on board before you start having to add more doors. And the 737 is actually kind of interesting because they make a variant that has so many people on board for these European budget airways, they had to add more doors to it specifically for safe egress. Now, these were mostly emergency doors, so these aren't the ones that they're using for boarding. But yeah, that's a really good example of something where you don't know what could cause the problem, but you don't care as long as you want to not know because it forces you to account for more things.
The point is that if you rely too much on post-mortem analysis, then you don't do this exercise. That's the comment. Not reliable. Thank you.
All right, Luis, you were next.
Oh, thank you, Alexander. Well, I'm sorry if anyone asked this before, please tell me. I'm just entered the session maybe 25 minutes ago. So I guess your presentation started with reference to robustness and two types of robustness, and somehow you said, well, one case of a system that has these two types of robustness is air travel, and I think you also mentioned elevators or as an example of things that are very safe, at least. And so I guess I just wanted to bring back the conversation to robustness, and what I mean by that is what other disciplines or areas of knowledge or in practice use the tools from air travel or aviation to give robustness to their systems, I guess. I mean, does that extrapolate to other areas? That's my question.
Oh yeah, absolutely. One of the first things that came to mind was actually cars have really changed how they design cars and build parts. They build certain parts now to be stronger than ever to protect passengers, and then they have designed other parts to intentionally be weaker as segments that can absorb energy in case of a crash, because most crashes are because you collided with something and you want the car structure to absorb that energy rather than the passengers' bodies. There's been a lot of research into that. It was also driven by development on rail vehicles as well and trains. One area has been ships. Redundancy of critical systems was something that was learned pretty early on after World War I, World War II, where they started having really complex mechanical systems, and they found out that if you took damage to one area, it would knock out pretty much everything that was there, so you better have had a backup on the other side of the ship. Nuclear power, I imagine, is something that's very, very interested in similar mechanisms where, you want multiple backups of the pumps for pumping the coolant, and for the shielding, you want multiple layers, and each one is robust and fault tolerant on its own, or fault deflectant on its own as well, and you just stack them up because you can, to ensure the absolute maximum of safety. As an aerospace engineer, I of course, almost all of my examples that I can think of are, within the context of my field, but I don't know. I'm virtually certain I've heard of other fields coming to aerospace companies and asking them, "Hey, can you teach us how you do this?" I can't think of any specific examples off the top of my head, but that's definitely something that I should take a look into.
Thank you.
Mm-hmm. Jacek, you were the next question.
Yes. Great session, great presentations. Thank you.
Thank you.
My question is about Space Force. I think when we started, it was purely politics and marketing and a bunch of bullshit. But I think that China probably doesn't have Space Force, but they are probably thinking about military use of the space. And what are the risks? This could be, it probably wouldn't be a black swan event because we can predict it, or at least we know that there is a risk of it. But what are the consequences to GPS? And I can envision that destroying GPS would paralyze the military.
Mm-hmm.
That's just one example.
Yeah, destroying GPS would be catastrophic. I would hope that the military has backup systems specifically in case of that, because they didn't have access to the GPS until 1980s, and U.S. military equipment, a lot of it is still left over from them. But just getting to and from work. I use GPS on every route I go on, even if I could do it blindfolded, just for traffic and stuff like that. But there is a risk. China is very much looking at the capability, like, using space for military reasons, just like the United States we have, Russia has as well. I'm not fully sure the extent of what they're looking to use it for. The US has used it very effectively for communication, for navigation, and for observation. Uh, there are all of these taboos, but also treaties against weapons in space and what is and is not allowed, and they're pretty strict. Russia has definitely used the space for military purposes, even though they've signed a lot of those same treaties. They've been some of their interpretations have been pretty loose. India is also looking to do it as well. The biggest risk that we have actually seen already play out has been debris of anti-satellite missile tests. So that's where they launch a missile from a ship, an airplane, or from the ground to hit a satellite to take it out. And every test has been a country shooting down their own satellite on purpose to demonstrate the capability. But the problem is that creates tens of thousands of small pieces in orbit that could collide with anything else that's up there, whether or not it's another military satellite or a satellite that's broadcasting, the World Cup to, parts of northern Canada or something like that. It's kind of indiscriminate. And that is, it's creating that can and has created a massive amount of pollution. And the U.S. has done a few tests. We've done so in a little bit more of a responsible manner than China, Russia, and India all have in the past 10 to 20 years or so. But that's something that concerns me, definitely. The thing about space that in terms of like military uses and the risk of it, that makes me feel a little bit more comfortable is it's kind of like the nuclear weapons thing, but even like more immediate. And that is, if you once you've hit something and made a mess up there, you've made it a mess not just for your enemy, but for yourself. So by making space unusable for an enemy, you can't use it either. Which, if we're talking about space debris, now if we're talking about like signal jamming and things like that, I'm not certain about that. I have no idea the capabilities there. We know that Russia could do GPS spoofing, but they're doing it from transmission towers here on the ground. My specialty is primarily, or my specialty has always been like commercial space, things like that. It's just been that's what I've been most interested in, exciting in personally. But it is it's something that is on everyone's radar who's working in space, whether you're a NASA scientist to military top brass, and that is what's China doing in space, not just in their civilian context, but their military one as well. And the Chinese government has a much smaller degree of separation between those two uses and branches than the US or Europe or even sometimes Russia does. Does that answer the question?
Yes, thank you.
Mm-hmm. All right, Gabriel, you had your hand raised next.
Yes, thank you. My question is about the Swiss cheese model. I've heard about that a lot of times before, but when you were presenting, I realized I don't actually understand how in practice it works. It's understandable to me looking at the past, just understanding that different errors aligned, but is it used as a process to prevent this alignment of happening, the alignment happening? So does it actually work in a way that each layer has to be literally misaligned or diverse in some way? I just realized that it's not clear to me how that works,
Yeah.
and if it's actually used for
Yeah, so the Swiss cheese model is absolutely used explicitly by name when designing and going through and analyzing systems. I think that more people could stand to use it, to be honest. But actually, both solutions that you have just mentioned have been used, where it's the same, it's identical implementations of the same systems, just with physical separation, such as certain control wires and things like that. It's the same kind of wiring electronic system. It's just one of them's on the left side, one's on the right, one's on the top, one's on the bottom. And a really good example of a fault-tolerant system like that is actually the computers on a lot of spacecraft. SpaceX was one of the first to do this, and that's the avionics on board. The computers that control the spacecraft are all computers and electronics in space are prone to bit flips, which can be a fatal flaw where the bits inside the computers are flipped by radiation. And this happens very frequently over the South Atlantic Ocean, but once you've gone past the Van Allen radiation belts, it can happen significantly more. NASA has a single computer. Well, what they do is they don't have fault tolerance. They just try to prevent them from happening. This is a simplification, but they try to prevent them from happening by putting the computers in very, very sturdy, rugged boxes that prevent the radiation from passing through and affecting the computation. SpaceX did away with that because it's actually very complicated to design one computer, but very cheap to just take up three of the same one. And what they did was they were programmed so that all three made the same calculations, and if there was a difference between the three, they would vote on which they would vote and see if two of them were identical and go with the double identical value, assuming that the third one had been affected by radiation and had produced an errant value. And then, and if it wasn't clear, they would redo the calculation, and so they can actually track when these things happen. And again, it's almost always in the South Atlantic Ocean. There's an anomaly there that's been well known for decades. But then on the space shuttle, for example, the flight control computers for the engines, they did both. So there were 4 computers controlling each engine on the space shuttle. 3 of them were identical, so that if one failed, there were at least 2 that could work. And then there was a 4th one that was developed by a different company with a different engineering team with the same requirements, but they were not allowed to communicate with one another on how to do things. So it was a completely dissimilar solution, specifically in case there was something that they could not think of happening, what could cause all 3 to fail identically. But if there was something that had caused it, that 4th computer would not be affected by it. And if it was something that affected all 4, you're probably dealing with something a lot more physical, like something very drastic. That's not a software issue. Um, the for on fly-by-wire systems and glass cockpits, which is what you see on most aircraft these days, which is instead of gauges and dials with needles and like old clockwork watches, it's all computer screens that display the information, but they still have those analog, sometimes pneumatically powered dials on board as a backup. It's a dissimilar backup because you absolutely need those to get back on the ground safely. So they have a system on board that is completely dissimilar in case there's an electrical issue. You don't need you don't need the computers to run these. Does that answer the question?
It does. For me, I didn't see the difference between this and just redundancy. So with this, it makes a lot of sense. Yeah.
Yeah, no, you stumbled on something very accurate, which is that sometimes it's just simple copy paste, and sometimes it is a dissimilar redundancy, and sometimes it's both. Ronnie, you've had your hand up.
Yeah, thank you, Alexander. Just continuing what Gabriel said about the Swiss cheese model, right? In security, we do it like really similar. We put like layers and stuff. And similarly, right, we create like policies and stuff like that to follow. But usually, vendors don't share like the magic recipe, right, to create these rules and be prepared, right? Does that happen in aerospace, or is like similar that, or is like better you guys share more information between vendors, or how does it work?
Yeah, so it really, I mean, every vendor has their own proprietary information, of course. Um, So Boeing isn't just going to post their blueprints online or email them off to Airbus, at least not intentionally, which things like that have actually happened in the past before. When I worked at Delta, we would sometimes ask vendors for information and they say, well, we don't give that out or you have to pay us extra for it and things like that. So there's always that there, but it's usually stuff that's critical information we like to see flow a little bit more freely. So maybe they won't give it to anyone, but if they know that you are a customer and you have purchased this or you've got something on the pipeline, they will share additional information with you, like drawings and blueprints and things like that. But I think that part of what you're getting at might actually be referenced by what I'm talking about, a good, healthy regulatory environment, which is where areas where there are known potential for problems, you want that shared and captured in the regulation because those affect everyone. So maybe it's a problem that only showed up on a A320, but you want that same rule to apply to the 737 as well. And so there's a lot of sharing of information between the FAA and the individual airlines and the FAA and the manufacturers and the airlines and the manufacturers as well. I remember getting emails from the FAA, Boeing, Airbus, people who made the trays for the tables, all sorts of different organizations. So yeah, there is a fair amount of communication flow especially when it comes to safety things like that. You don't want to keep that secret. And if you've got a safety issue that bumps up against proprietary information, you've done something really strange or wrong. Does that answer the question?
Got it. Yeah, totally. Just out of curiosity, what's the biggest effort to make stuff public? Is there any effort here?
I'm sorry, what's the largest effort to do what?
Yeah, to make like the policies and all this stuff public, for the public. Is there any effort?
The best way to the name for what the FAA does is called an airworthiness directive, an AD. That is a notice for pretty much everyone who operates a particular type of airplane, and I have seen them apply to specific planes, say such as these three serial numbers. Hey, you have a fault with these three, and even though only one airline operates those three, that AD is going to be passed around to everyone. And then I've seen them cover like any plane made in this particular factory, regardless of model, and within this period of time. And they've ranged in severity, be like, hey, please make sure you change this part every like 5 years to all of these are grounded until further notice and that they're fixed. So airworthiness directives is one of them. There's what's called the self-disclosure channel, and that is how airlines disclose information about faults to the FAA. So FAA issues directives, airlines issue disclosures. And then there's, you have things like symposiums and meetings and conferences where these things are discussed, in a more like kind of like this fashion right here. Meetings will be set up with specific agendas to target specific issues. And then there are communication channels where individuals, even not just companies, but individuals can raise safety concerns in either an anonymous or non-anonymous way, based off of their own observation. And those are things created with paper trails. And sometimes those are sent to people whose job it is solely to look at safety concerns that have been raised by users and see if it's a known thing, an unknown issue. Is it something that needs to be elevated immediately? Is it something a long-term issue? Unfortunately, every airline seems to have their own sort of name for that thing. And off the top of my head, I don't know what the FAA's one is named anymore. It's been about 5 years since I've worked with that, and it's been even longer since I've had to file one. And luckily, I've only had to do so once in my life, and it was for um, something that I would describe as non-critical.
Got it. Thank you so much, Alexa.
No, Luis, you've had your hand raised again.
Oh yeah, thank you.
Mhm.
So I guess this goes in line with the previous question that was raised. So there's aviation is like a global system, the way I see it, right? So uh, yet the info that you used is mostly from the US, and you said that the US is, at least in the US, it is very safe to travel by plane. Um, so I guess, is there any specific info about other countries? For instance, I live in Colombia. Just out of curiosity, I would like to know if it's I suspect it's not as safe as in the US, but maybe what's the difference there? And yeah, I think even though it's a global system, there are differences in countries. I guess where where do where does those where do those differences come from? Or if places countries has less safety than others in terms of air traffic, why would that be?
So, my first response to that is going to be enforcement, because these countries very largely have the same regulations to the point where when I have pulled up regulations from the European um, aviation authorities, it still had the FAA watermark on it because the FAA and the Europeans um, work intentionally work together to make sure that their rules are harmonized, and if there's a change they consult one another specifically for that, so the numbers that I've been citing apply. The you can assume similar safety performance out of any airline that falls under EU regulation. Um, and A lot of air carriers actually send their planes overseas to China or to Ecuador, Mexico. Those are all places. El Salvador all have maintenance bases that maintain U.S. airplanes doing heavy maintenance because they're subject to the same rules, and that when the plane is done, they're inspected here to make sure they met the same standard that if they had been done here in the U.S. Um, so a lot of it comes down to enforcement. It's how much can a pilot get away with before something gets caught, and that has been a problem. There have been issues like that in South America before. Africa and Southeast Asia have all had airlines and operators not follow the book very well. One thing that you can do to kind of hedge your bets is see if the air carrier operates into the EU, into the US, because if they do, they become their planes, those aircraft in particular are under partially our jurisdiction, not to mention that um, they're all built in either Toulouse or Seattle, with a few exceptions like Mobile and Hamburg. Um, that's largely how it's how there's how some areas can be a little bit less safe, and it's enforcement of it. It could be a cultural thing as well. It can be access to resources for maintaining the fleet. But oftentimes, it's a cultural thing as well. There have been some airline operators from countries that would be considered developing that have absolutely fantastic records, and then there's some that people have a bad reputation as being unsafe. They've had accidents, And then there are air carriers who are not allowed to fly into the EU. The EU will list certain airframes as being deficient, or an entire airline's entire practice and model as deficient and not safe. Air Koryo from North Korea has been on that list for decades. There have been a couple of airlines in Southeast Asia, Africa and South America, and Afghanistan that have all ended up on that list before, as well. But on the other hand, as well, there is a global industry for the maintenance of aircraft, and they all have access to the same. They ideally have access to the same parts, the same instructions, and the same training necessary to maintain aircraft around the world. I know that at one point when I was working at Delta, the nearest station that had that part was Tokyo, and because of this logistic network that was all around the world, largely because there were planes being maintained in China, we were able to get it the next day, even though it was we were here in Atlanta trying to figure out where the nearest one was.
Thank you. Yeah, that's very helpful.
Mm-hmm.
I was wondering, this seems like a very safe system, like and very that learns from mistakes. I was wondering if there was anything interesting to know about we've talked about like working with problems, right? But I was wondering if there was anything interesting to know about the system which identifies and diagnoses sort of the problems, or is that the easy part, sort of identifying the problem which led to the disaster or to the failure?
Yeah, it really depends on how much evidence is left behind. Sometimes, if you're talking about the problem being a particular crash, sometimes it's hard to see if it's a cultural or systemic problem. You'll see evidence of it, but you won't necessarily see the overarching problem as well. And it's really like cultural problems within an organization are a lot more difficult to see because it takes a long time to manifest themselves, and you can they're not always explicitly driving errors and stresses on the system. Sometimes the determination of what causes a crash is incredibly easy, depending on the nature of it, because the airframe hasn't been completely destroyed, the black boxes are still there, the pilot survived and can provide testimony and things like that. And there, the challenge is really just making sure the solution gets disseminated and implemented. So, you have a crash caused by, let's say, a failure of part A. You want to make sure that version B of that part is strong enough and is a suitable replacement. So you have the challenge there. It's making sure the job gets done correctly, and it's then following up and make sure that everyone who needs to know about it figured it out through the airworthiness directives, through direct communication between the different departments of all the different parties that and then making sure that it gets installed in every single aircraft. And a lot of that is paperwork issues sometimes as well. But yeah, sometimes it can be very difficult to diagnose a problem. There are crashes out there that should have been absolute game changers, but where not a lot happened afterward because we don't really know exactly why it happened, or there was no readily available solution that could have prevented something like that didn't introduce even larger problems. For example, there was an Air Egypt flight out of JFK, I think around 1999, where again it was a pilot suicide, just absolutely horrific crash, and there was a cultural issue with it, and that was Egypt Air, country where that sort of thing is extremely frowned upon, and the authorities there would not and still do not acknowledge that that was the cause, even though it was very, very obvious that it was, and all the evidence pointed to that and really nothing else. And the U.S. authorities said, well, it was that, but no one really knew what to do to prevent it. Is there a way for one pilot to overtake the commands of the other? Well, you've now opened up an even more risk. Does that answer the question?
Yes, thank you.
All right, Amin, you've had your hand raised.
Yes, so as I hear everyone talking, and I was thinking about, so I'm coming from a biomedical background, and as you know, there is a lot of things that are bio-inspired, right, in AI, certainly in aviation, like in terms of aerodynamics, I believe, and other systems in aviation. So I was thinking whether there is some work done in like in the Bioinspired kind of framework in terms of tolerance of yeah I'm blanking on the term, um, not tolerance. So you give us two fault,
Robustness.
yeah, you give us fault
Yeah.
tolerance versus something else. Sorry, I'm blanking on the jargon here.
Yeah, so I'm not aware of anyone who has done that on commercial aviation. I know that going back to NASA, they have a very large biomedical scientific team and basis, and life sciences on board the space station is something that's a very big deal. And
Just to be clear, Alexander, I'm not thinking about biomedical application. I'm thinking about aeronautic and flight systems that are bio-inspired, you know, like
Bioinspired, yeah.
yeah,
Yeah,
that's what I'm
it's
talking about.
yeah, I don't know of any explicitly since maybe the early days of aviation where people were literally looking at birds, not just the shape of the wing and how they flap, but the structure. People were looking at the bone structures as well, and trying to mimic that. But that's something that I should take a look at and see if I can find something. There's no way that there has been nothing done in that regard. I'll say that much. I'm virtually certain someone has applied it before. Let's see. Are there any other questions that we have? Jorge, your hand's raised.
If I'm given an option, I'll double dip.
Mhm.
Elon Musk is teaching cars to navigate by analyzing video, and he has zillions of hours and miles that he's analyzing and learning, getting the AI to understand the real world through video. Is this a similar thing? Is this being done in the same way or analogous way in planes? Because I imagine NTSB or somebody like that could be looking at analyzing dialogue between pilots and video from the cockpit and telemetry and so on. Is there anything being done? Because that would have a significant gain, I think.
Yeah, so more and more aircraft now not only have for a while there has been a requirement to have audio recordings of what's happening in the flight deck. Um, which was a big controversy because pilots 50 years ago, when that was introduced, thought it would intrude on their privacy. The same exact thing happened again a couple of years ago when certain airlines started putting video in the flight deck to record how pilots behave. And that has and can be used for analysis of an incident to see, hopefully this Air India flight has a video to see how those switches got moved into the cutoff position. I really hope so, because that'll answer a lot of questions. Um, I, um, I don't know if anyone has ever, pulled, video from a flight that operated just fine to see how it works. But there has been observation of stuff done, in simulators where they specifically are putting pilots into stressful situations to see how they respond in a very safe, constructive environment. As for more navigational things, which is what a lot of the cameras in Tesla does, um, this is it's not quite as suitable for aviation because eye visibility for navigation and avoidance of other airplanes is a lot more difficult because when you're navigating with stuff on the ground by eye, you need really large landmarks that really stand out. And when you're looking to avoid other aircraft in a collision by eye, you're sometimes closing at over 1,000 miles per hour, depending on what speed you're moving at the angle and the altitude. So that isn't the most reliable system to rely on cameras and things like that. And Tesla's had that problem because they rely only on cameras and not LiDAR, where other manufacturers have been using LiDAR. Tesla has had several accidents where the camera did not detect something that LiDAR could have. And aircraft do have other types of non-visual sensors like radar on board for weather and things like that. And then there's radar on the ground to tell pilots when and where there's other traffic in the area and to be mindful of it and maintain their separation. Um, Now, small video cameras, not for like AI purposes or for self-navigation, but a lot of airplanes have cameras in the tail now and in the near on the belly near the landing gear too, and help to really improve visibility, especially while on the ground while taxiing. And that has been a very useful thing. The A380 has it, 777-300, A340 600, because they're all incredibly long aircraft and they just are really helpful at visual orientation. And I particularly like when I'm on planes with those cameras because oftentimes you can stream them from the back of your seat as one of the entertainment options. Does that answer the question?
Yeah, sorry.
Do we have any other questions or comments, concerns? Unrestrained praise?
Yep. Thank you so much, Alex.
Criticism, I'll send you an email for criticism, an email address. All right, thank you, everyone. There have been a lot of very good questions, and that I've been excited to answer. And I've got a couple of things that, if you show up to a future institute, I will include in my slides because they've been very thought-provoking and have. I've done this about seven times now, and in doing so, have practice and experience and have improved and made my presentation more robust. In no small part, thanks in no small part to the questions that I have gotten every session, including this one. And if you have any further questions after today, I posted my LinkedIn in the slides. I have uploaded them to the file. Feel free to reach out there. I'll post a link maybe during the conversation tomorrow, especially if this topic comes up. I'll continue to be here for the 8:30 to noon sessions for the rest of the week. So thank you everyone for joining. Have a fantastic rest of your afternoon or morning, depending on which hemisphere you are. And I look forward to hearing back from everyone.